Okay, welcome to the second day of second week of ST4 2020. We will be started off by black hole information paradox or information loss paradox in ADS2 by Adwait. Over to you, Adwait.
Yeah, thank you. So this I've just pasted the summary which I posted on Slack. So this is like a short summary, but this is really all you need to know in order to understand what I'm going to say next. So first of all, we discussed about the classical aspects of black holes, and we show that there was a hint to identify the surface gravity with temperature, and also the area with horizon, area of the horizon with entropy. But then when Hawking discovered that black holes radiate, then the area of the horizon might decrete, and that creates a problem for the second law. And to fix that, Bekenstein had introduced generalized entropy. And this generalized entropy is still a coarse-grained entropy in the bulk, but we'll see that later on by using quantum RT and Rutha-Kanaki prescriptions. If you apply generalized entropy, so Bekenstein thought the generalized entropy formula should be applied to black hole horizons. In the sense, we are computing area of the horizon, and the S bulk term, which was the second term, is computing von Neumann entropy of the fields outside the horizon. But we'll see later that if you apply the same formula instead of horizon to some special surfaces called quantum extremal surfaces, then that exact formula can compute fine-grained entropies, and we'll see it later. Now, we also discussed the difference between fine-grained and coarse-grained entropy, and if you haven't understood what I was trying to say, it's okay. You just have to remember that fine-grained entropy is a measure of entanglement. It tells you how much your particular system that you are focusing on is entangled with its environment. And coarse-grained entropy is a measure of degrees of freedom contained in that system. So how many degrees of freedom, or if you're working with lattice system, it's basically telling you how many lattice sites do you have, or how many spins do you have. So it's a number of degrees of freedom. And as a system cannot get more entangled than the number of degrees of freedom it has. So if a system has n, let's say n spins, it cannot entangle with any other system for more than n spins, because it only has n spins. Hence, a coarse-grained entropy of a system. So let me write it here. A coarse-grained entropy, I'll always put a subscript if it's a coarse-grained or fine-grained. A coarse-grained entropy of a system, which is described by rho, is always bigger than the fine-grained entropy. Fine-grained entropy of the same system. So this is the equation you have to remember.
Adwait?
Yes.
So from the Slack discussions, you might have seen, like, some of us were wondering if this usage of the word one-point function is appropriate or not.
I'm just yeah. So I agree with your discussions. I hadn't thought a lot about it because I was never really going to use that definition.
Okay.
But the mistake I was making is I was already selecting a subset of observables for you, and those were one-point functions.
I see. I see. Okay,
it's not like you have to use one-point functions, but you have to use a subset of. I think Nirmala has written a statement on Slack, and I think that's the most correct version of what I wanted to say. But we are never going to use that definition, so it's fine.
But are you calling this trace rho OI as like one-point function, or is that like expectation value of some general
expectation
operator?
value of a general operator?
Okay.
Yeah.
Thanks. Yeah.
Okay. And when I'm considering so these operators are also supposed to be coarse-grained, and that is the meaning of, if you have one-point functions, it is inherently like an operator confined to a subsystem. So that operator only has a support on a particular subsystem of the Hilbert space, and hence it's automatically coarse-grained in some sense. So so just saying one-point function covered everything, but that's not the condition. You can choose more general operators, but they should be coarse-grained operators. Then we discussed about nice slicings, and we showed that nice slicings is basically a construction where quantum gravity effects can be neglected. And we also showed that we didn't show it, but this is a
question.
Yes.
Yeah, when you said coarse-grained operators, did you mean what should Excel think of? Like, you say that,
So they only supported over part of the Hilbert space.
that's what coarse-grained is.
Yeah.
Okay. It's not like I have I have an accuracy to which I can measure. That's not what I mean.
I think what you're saying also can be understood as what I'm saying. That if something is giving you an approximate answer, that also means that it only has support over a part of the Hilbert space.
Okay, thank you.
This is a statement which is true, that any chart, any coordinate system that covers interior and exterior of a black hole has to be time dependent. And then we also showed that a particular construction of a chart of slices, of nice slices which cover interior and exterior, and we wanted to make it as static as possible, as time independent as possible. And we sort of argued that it's the connector region, is the region that connects exterior constant slices to interior constant slices. That is the region that is necessarily a time dependent region. Another thing I said something wrong in the last lecture was this, that Anish was worried about what is happening with this slices. So what I had done was I had drawn these interior slices here, and then there are exterior slices, but I should have drawn a left slice also. And then when I connect them across, I should be connecting them like this. So these two regions are connector regions, and that's how you connect them. And then you'll see that the expansion only happens in these regions. Okay. And now you're not including I plus, it's just I zeros from both sides. So, and then, so this is just to, so the slices that I am constructing are constructed in a way such that time dependence only is in the red part. But you could always construct general slicing, which is basically these, so this is t equals to 0, but then you can just construct a slicing which just goes like this and goes on. And this is also nice slicing, so that's fine. But this slicing has a time dependence almost everywhere, but the slices that I have shown have only time dependence only near the horizon. So that is one part. And okay, so this is a statement I'm going to make, and if I get time, I really want to get into this. I'll tell you an example where you can find this. But the fact that whenever there is whenever space-time slices are expanding, there's always particle creation. Okay, the way you can see this. Okay, there's no, okay, I have to explain more in order to see this, but for just take it as a fact, and if we get time, I'll describe a very nice example which is given in okay, this is bad, which is given in Birrell and Davis. So let me just write down a reference here, and I'll just go ahead to explain what the state looks like. So in Birrell and Davis, look at section 3.4. It's a section about expanding a particle creation in an expanding cosmology. And there it's explained how time dependence in a geometry actually creates particles. So let's if there is a confusion here, I'll come back, but I don't think it's exactly required to know this mechanism, but just the fact that this mechanism exists. And now let's look at
I have a question about choosing these nice slices. Like in the last slide, whatever you have shown for Schwarzschild, like Penrose diagram of the Schwarzschild black hole. Yes. So they are like I think probably you want to do the same thing for ADS2 black holes kind of thing. But I think like in two-dimensional case, when you have in Lorentzian signature, say you have only like one space dimension there, you know that I zeros, whatever you are telling, those are really 2 points, and like the horizons are really points, not in a case like sphere or anything. So there, how you will choose this kind of slices in Lorentzian ADS2 black hole or Lorentzian immediate flat space black hole also?
Oh, so actually what I'll do is there's another concept. I mean, what I'll do is I'll take ADS2 black hole and I'll attach some baths to it. externally to its boundaries so that radiation can leak out. And I'll extend the space-time, I'll make a bigger space-time, and I'll embed that whole space-time into a flat space-time. This is actually the novelty of the construction which these people have done. So I'll specifically get to that. So maybe you can ask me then.
Yeah. So there it's been like, I was just trying to understand what is the horizon,
how is horizon defined?
Means in two-dimensional black hole, I think the horizon is just 2 points are equal to, or just maybe 1 point are equal to 2 cm, right?
Yes.
So they are like if you are want to cross the horizons and anything, how you will choose the slices in two-dimensional black hole, this is little puzzling me, but I think maybe you will explain later.
Yeah. I'll get there. So so this is the scenario, and let me paint the scenario. This is a Penrose diagram of a evaporating black hole. Okay. And let's say of like a black hole which is formed from collapse and then it's evaporating away. And as we have shown that you can almost say certainty that across horizon there's a lot of pair creation, and this pair creation is what I said you have to assume that this is how the pairs. So let's say let's consider this black slice, which is a slice at some earlier time, and it's you can see that on this particular slice there's no horizon. And let's say there is some pure state here, okay, and let's call this pure state as some let me call it psi matter. Okay, there's some matter state over here. Okay, and then let's draw 2 more slices just to see what is happening. So let me draw a slice which just goes like this, and let me draw another slice which is up here. Okay, now what happens is and let me label these slices. So let's say this is slice number 1, slice number 2, slice number 3, and in your head you can think of these 3 slices as time steps, some sort of time steps, one slice to next slice to next slice, and this is how the system is evolving. Okay, so what happens is there is a pair creation across. So at step 1, the state looks like psi matter. Okay, this is what a state looks like, and this is a collapsing state, and it's a pure state by construction. I mean, we are just saying that we threw in some matter, so we exactly know what the state is, and it's a pure state. It's going there. Now, what happens is let's look at what the state looks like on the 2. Slice number 2. Okay, and I'm basically at this point I'm postulating this, but I can give you references where this is explicitly worked out, and you can see that this is true. But what happens is the state at slice 2 looks like this. So it's approximately like this, in the sense in the leading order approximation, this state looks like this. There is psi m, which is original, which was original state, and it's tensored with plus, and let me call it A1 B1, and let me define what A1 B1 is. So a plus AB is 0 0 plus 1 1 by root 2. Okay, so what am I doing is that let's say you have a quantum field theory which is evolving. Okay, and the quantum field theory has a spectrum, and what I want to tell you is that whatever these new 2 particles are going to be created. So let me draw these 2 particles. So there's one particle just in here, the second particle just out here, and let me call the inner particle as A1, okay, and the outer particle as B1. And the point of this approximation here is that it's telling you that the state of these 2 particles is maximally entangled. Okay, and just to show what a maximally entangled state looks like, I'm approximating it by a 2-state system. But generally, it won't be a 2-state system. It will be some quantum field theory which has continuum states, but all of them will be maximally entangled in this way. Okay, is it? So this is how the state looks at the time step 1. So what have we assumed here? First of all, when I write down this state, what I have assumed is that the matter, whatever new pairs are being created across horizon, and I'm calling them A1 and B1, those pairs are not entangled with initial matter, right? Because I'm clearly writing it as a product state. Okay, so the collapsing matter is not entangled with the newly formed pairs. This is assumption number one. It's not an assumption, you can really prove it by looking at actual Hawking state. But this is how the state looks like at the leading order approximation. And let's look at how the state looks at the state number at the time step 3. So at time step 3, what happens is the two pairs which were formed earlier will just move away from the horizon. So one is a bit inside, the other one is outside. Okay, and two new pairs will be formed in here. Okay, so this pair here, this is A1, this is B1, and this is A2, and this is B2. Okay, and the state at time 3 looks like this. So it is already a matter state, and it's we have the original state, which is an maximally entangled state of A1, B1, and the newly formed paired are again maximally entangled with each other, and they are in a product structure. Okay, so the first assumption was that newly formed pairs are not entangled with matter because there's a product state structure. The next assumption is that newly formed pairs are not entangled with old pairs, and they're neither entangled with the matter. Okay, are these things clear? I can repeat it again, but yes.
I have a question. So, which is like, can you tell me like what Hilbert space do these states belong to? Like, what is the Hilbert space structure?
Oh, we are looking at a quantum field theory on this background, right? So background is fixed. Whatever this background is, this Penrose diagram looks like, and we are looking at a quantum field theory on this. So whatever quantum field theory you want to consider. If you're considering graviton, then it's a Hilbert space of the graviton. If you're considering, it's a Fock space.
No, what I'm trying to ask is this A1, B1, right? Mm-hmm. So that has some HA tensor product HB kind of Hilbert space, right? To be able to write a state like that.
Yes.
So what is HA and what is HB? Like, is it like inside there is a Hilbert space and outside there is a Hilbert space, or like, does it depend on the direction those particles are going in? Like, how are these Hilbert spaces?
It kind of depends on the direction in which these particles are going. But okay, so let me say it in this way. So if you create an excitation on a slice, it travels along the slice in the sense in time, but it travels along the slice. And then at any point, you can pick a point in the slice and just divide the degrees of freedom across this. So these excitations are not really localized to any part of your slice. These excitations can go from one part of the slice to other part of the slice, and it depends on where you are dividing the slice, and that depends on what is the tensor product structure. In the sense, okay, let me just draw a caricature here that you could have a state. Let's say you could have a state which looks like something like this. There are two bumps here, and there's nothing here. So two wave packets here, and then you choose to divide the Hilbert space along this direction. Let's say at this point, then entanglement between this and this will be entanglement across this surface. Maybe I should draw it in some color. Yeah, entanglement across this surface is almost nothing because both the particles are just here and they are entangled with each other. But let's say one of the particle travels and goes to the other side, then the structure would look something like this. There is a bump here, and then there is a bump here. Okay, and now if you choose the same point to divide your Hilbert space, let's say, then you will see that you'll see some entanglement because one of the particle excitation is on one side and the other particle excitation is on the other
side. Yeah, that's okay. And can you also tell like what went into these proofs? I mean, like, what do you mean when you say it is proved?
Oh, the people have taken 2D dilaton gravity models and explicitly written down states.
Okay.
And there are other computations, like people have looked at entanglement structure across the horizon, and they always find it maximally entangled pairs. So the 2-point function is supposed to have a certain form, and if the 2-point function has exactly that form, then you can deduce that it's a maximally entangled across the horizon, and people have done this.
Okay, thanks.
So
Adwait, would you be able to say a bit more about this 2-point function thing? Like what?
I mean,
because that's a very precise statement. No, I'm totally like ignorant about these things.
okay, I have not really studied it, but it's one of the Suvrat's recent paper where they use this 2-point function as a diagnostic to understand whether horizons are smooth objects or not. In sense that yeah, so you could just take how do I say this? Okay, let me try to say a bit more. So if you take a Minkowski diamond, okay, let me draw an RT diagram. If you take a Minkowski diamond, and if you put let's say this is X direction and I'm working in 2D, and then you put some ground state over here, okay, and then you want to see how you want to see, let's say, how what is the entanglement entropy of the half line, in the sense you are going to divide the surface across this this 0, 0. Okay, so right now, because it's ground state, there is no excitation, but then if you expand in Rindler modes, you will see that Rindler modes have Rindler modes are basically these lines, right? Boosts in Minkowski space. Then you'll see that if you expand the same Minkowski ground state in terms of Rindler modes, then it's really it's a thermophile double in terms of Rindler modes. Okay, so then what will happen is there's a mode here, which is entangled with a mode here, with a thermophile double like entanglement structure, and a 2-point function can detect it. A 2-point function can tell you that this is the structure, and that's basically tells you what is the structure of entanglement across any surface. But this is a very general statement. I'm just
So when you say 2-point function measured by like
what is the 2-point function of, right?
2-point function of fields. So okay, so if I have a field which is being expanded in some Minkowski, or let's say Rindler modes, okay, so you have to expand it in right and left Rindler modes, and then just let me write it as not in some Rindler modes k plus complex conjugate. Let's say this is the expansion in the right Rindler modes, and there will be a similar expansion in the left Rindler modes. Okay, then you just, and this is also right and left, then you just find out what is the 2-point function of this guy and this guy across the entangling surface.
I see. Thanks.
Okay, I'm making vague statements, but that's the point. I don't want to go in more detail here. Maybe I can just I can put the paper in the Slack to show that what
Yes.
it is.
okay.
But that should help. Okay, so yeah, so this is what we were discussing. So let's do a small experiment here, that after the time in the second time slice, try to find out what is the entanglement across the horizon. Okay, so at the second time slice, the way there are 3 excitations in your state. There's matter, okay, plus the A1 particle, and it's is it visible? Sorry, I'll just write it in white.
I think Karan has a question. Karan, go ahead.
Yes.
Yeah, can you hear me?
Yeah.
Yeah, I'm sorry, I'm a little confused still. So on step 2, you said that there's A and B which are maximally entangled, reduced on this fixed background. What is happening in step 3 exactly? Like, what's your comment on how A1, B1 and A2, B2 are related? Like, they're 2 different maximally
They're not entangled
pairs?
with each other. So there are 2 different maximally entangled pairs.
Okay.
But
okay.
so okay, just to establish some sort of words, I'll call A1 B1 as early radiation, A2 B2 as late radiation. Okay.
Okay, but there's no entanglement between A1 B1 or A2 B2.
No.
Okay, fine. Thanks.
Yeah. So this is what you have. There's matter, and there's A1 particle, there's B1 particle. Okay, and as A1 and B1 is maximally entangled, if you really just find out what is the entanglement entropy, a fine-grained entanglement entropy of B1. Okay, in the sense I just divide the system across horizon, and I want to find out what is entanglement entropy of B1. I'll basically just get log 2, right? because of this state. This state is maximally entangled state between A1 and B1, and I'm just the only thing that is entangled between a system, these two bracketed systems here, are the pairs A1 and B1. So whatever is entanglement between them, that is the exact entanglement I'll get. So at step 1, the fine grained entropy of the radiation, whatever is going out to infinity, I'll call it radiation. So fine grained entropy of the radiation, is that clear? I can repeat it if it's not clear. Okay.
Repeat it, please.
Should I repeat it?
Yeah.
Huh. So okay, maybe I have to drop this. You see, you just look at the structure of state number 2. So if you look at structure of state number 2, this plus state is just this state here. Okay. So the matter is not entangled with anything else. The matter is just whatever it is. A1 and B1 are the only things that are entangled with each other. Okay. So I'm dividing the system as this. I'm dividing a part of the, I'm dividing in my whole system into 2 parts. One part I'm calling matter plus A1, and the other part I'm calling B1. And that is really a division across the horizon. So if you see here, the thing which is in here is matter plus A1, and the thing which is outside the horizon is just B1. Okay, and that is the division I'm doing. And the only entanglement from the things which are inside the horizon and things which are outside the horizon are coming from this structure, which I've written here. And if you take this structure and if you find out entanglement entropy of one of the party by the formula just trace rho log rho. So first what you have to do is you have to take this state, you have to reduce it on just B1, and you'll get reduced density matrix for B1, and then you compute von Neumann entropy of B1. And that answer is just going to be log 2, because that's just clear from this state. The structure of this state always gives you entanglement entropy log 2 of either A or either B. Okay. So that is okay. So that is one thing. So now let's look at the second. Let's look at the second part. Which is the third time step. And the third time step, our state was the matter tensored with the 2 particles, which I was calling early radiation, and then there is the late radiation. Okay. Now again, what is the system? The system inside the horizon is matter plus A1 plus A2. Okay. And outside the horizon, the system is B1 and B2. Okay. So now again, I divide the system across the horizon, and I again, so whatever is outside is always radiation. Okay. In the sense of everything that I can collect to infinity, I'm going to keep on calling radiation. So the radiation comprises of these 2 particles, B1 and B2. Now I want to find entanglement entropy of B1 and B2. So the same procedure, I have this state, I can find reduced density matrix for the system B1 and B2, and I compute von Neumann entropy of that system. And it's very obvious from the structure, the fine grained entropy of B1 union B2 is going to be twice of log 2. Okay. Now that's just happening because this is, am I naming it correctly? Yeah, this is this is happening on the third slice. So what I have divided now is matter plus A1 plus A2 is one system, and B1 and B2 are going off to infinity, and there's some other system. And I'm dividing them and just counting the entanglement between them, and that gives me 2 log 2. And now I claim that if you just go to some nth step, if you just go to some nth step, then your state on the nth slice is always going to look something like this. That there's matter, and then you just tensor all of these things. There's always a pair production across horizon, and all of these pairs are maximally entangled with each other. So now at this point, if I again divide the system, I have matter plus I have, some more AI, and I have some more BI, and all of this system I'm going to call radiation. Okay. So the fine grain entropy of the radiation on the nth step goes approximately as n log 2. Is this clear?
I think Supu has a question.
Yeah, so Adwait, I'm a bit confused because I mean, so far you have been saying this thing is proved, but are you assuming like the Hilbert space is factorized across the slice, like you can split it somewhere and the Hilbert space structure is factorized?
Yeah.
I see. Okay.
I mean, whatever I'm saying might not be true because I'm just trying to tell you what the problem is, and then we can think about where I might have gone wrong. But
yeah, no, I'm just confused because you're saying that all this has been proved. I mean, if it's been proved and if it's also contestable later.
People, I'm just saying that the problem of information paradox was, there are papers which have conclusively sort of shown that a black hole destroys information. And okay, let me postpone this to later. And your question is more relevant, but I'll comment on it. Okay.
Okay.
So this is what is happening. Okay?
I have a nice question.
Yes.
So you're talking about this nth step entropy, right?
Yeah.
But in this continuum limit, how do I think of this nth step? Do you understand my question? We are talking about these different time slices, and you're saying in each of these time slices there are these new pairs being created, and they're maximally entangled with each other, but not with early radiation or the matter, right?
Mm-hmm.
But my question is that, see, it's a continuous. I can continuously slice my space-time, right? And at every step there will be these entangled pairs created.
That's true.
So how do I see this n? What is this n in my space-time?
Oh, it's time. It's just, you're looking at things after t, some time t. So n just is.
So basically what it says is that this fine-grained entropy will be proportional to the time.
Exactly. So we'll in the model I'll describe later, we'll exactly show the result that entanglement entropy of the radiation naively by all the arguments I'm making increases linearly.
Oh, okay.
Okay. So this is this sort of a linear growth with respect to the time steps in the entanglement entropy of the radiation. Okay. And what is the problem with this? The problem is, let's look at this diagram here, that after so now first of all, the first assumption is that let's assume that this happens. This keeps on happening forever, and this keeps on happening until the black hole evaporates away. Okay. So once black holes evaporates away, you are at some final stage here. Okay. This is the final slice. Let me right, where you don't really have any black hole, and black hole has completely been evaporated away, and now what we are saying is there's some radiation here. So all these particles B1, B2, all of them are now on this slice. Okay, so there are a lot of particles here which we are looking at, which are in the space-time. And we also sort of conclusively, not conclusively, but we argued that the entanglement entropy of all those particles is going to be n log 2. Okay. Again, if you have questions, please ask, because this is just conceptually I am going to build upon this. So what I've shown that as time goes, it just keeps on increasing with whatever time step, and at a point you reach where you have a radiation, and the entanglement entropy, the fine grain entanglement entropy of the radiation on that slice is n log 2, but there's no black hole. Okay. Now the only way a state can have a non-zero entanglement entropy, non-zero fine grain entanglement entropy, is that if the state is mixed. Okay. If the state is pure, then the entanglement entropy is 0. But what we showed is that on this slice, the fine grain entanglement entropy is okay. maybe I'll write it here. Find the entanglement entropy of the radiation after the black hole evaporated away it just keeps on growing. Basically, it's an ever growing entropy. Okay, and more importantly, it's non-zero. So that what does this tell us? It tells us that the state on the final slice here is really a mixed state. Okay, because it cannot be pure state. If it's a pure state, the entanglement entropy of that state cannot be non-zero. It has to be zero.
Adwait, I have a question. Like, should we really assume that the full black hole evaporates, and up to that point, we can still believe that we can treat gravity as a background, and quantum field theories are in that background moving? Because really, when its size becomes Planck length kind of size, you cannot even use this thing. You have to probably look for quantum gravity.
Right. So the argument I'm presenting has this particular loophole. That I'm assuming that everything I'm saying happens till the very end of the black hole, but okay, all right. But first of all, I've shown a very very first contradiction with black holes is that they are point. I mean, inside the horizon is just a point somewhere in. Okay, the singularity is just a point, and most of the black hole is just empty. So if you throw in something, the matter just goes and it goes inside the singularity and it just goes away. Okay, that's the first absurd thing you feel about black holes. The second absurd thing, it's an improvement of the absurdness of black hole, is this, that you can see that the entanglement of the radiation just keeps on growing. So it's not, first of all, it keeps on growing, and it's non-zero even when the black hole is not there. So if entanglement entropy is not non-zero, the state has to be mixed. Then what have we really conclusively said? What we have said is I started with a pure state psi m, but I ended up with a mixed state. Okay, and it doesn't ever happen under unitary evolution. The unitary evolution always takes pure states to pure states. Okay, so what we have sort of shown is that the pure state that we started with is really going to a mixed state. Okay, and this is a very naive argument, and it's okay if you're not convinced, because yes, there are loopholes in this argument, and I'll talk about what are the loopholes. But we'll improve upon this argument. This is the oldest version of black hole information paradox, but then there are newer versions. So let's talk about what are the loopholes. First loophole. The first loophole is, as someone has pointed out, that we assume that this evolution goes all the way up to the final slice, or all the way. I have assumed that whatever I was saying even works very close to the black hole on a slice which is here. Okay, so one scenario is that you could say that maybe what happens is that black hole never really evaporates away. There is something that stays back, and these objects are called remnants. Okay, and you could say that these objects might have so much entropy that they somehow purify. And these remnants necessarily have to be quantum gravity effects, because the last slice is going really close to the singularity. Hence, a remnant has to be some quantum gravity object, and more than that, that remnant has to have huge number of entropy in order to purify the state. Because what we are going to say is that when the evaporation process ends, you have a remnant and you have huge radiation, and they have to be entangled with each other, and that is the only way radiation can have such a large entropy. Okay, but the point is, remnants are really problematic objects in the sense that somehow if remnants do exist, then you should detect them in LHC and they'll cause huge problems. And also, if this is an asymptotically flat setting, but what remnants are saying is that it's a very low energy object, but it has huge entropy, in the sense it has huge internal structure, it has huge internal states. And in ADCFT, we know that using ADCFT, we know that at any energy, below any energy, you only have finite number of states. So you don't really have so many number of states that it can just purify this large number of large entropy. Okay, hence remnants are really in general problematic, not just to this problem. So people generally assume that remnants don't exist, but there is no real proof of this. So this is first comment. Second comment is that what we did was a leading order state computation. In the sense, all of these states I have written down are really toy approximations, and you could try to include more and more perturbative computations. In the sense, we could take, you know, maybe you could take higher order corrections for the state in G Newton, or we could start taking graviton effects into account, and we see that how this state gets modified, because the whole problem which I described is only coming because the state has this particular structure. The structure of the state is that the new pair forms are maximally entangled, the new pairs are never entangled with the matter, and new pairs are not entangled with the old pairs also. And this structure is a very universal structure of the Hawking's state. Okay, and you could, and whatever I have written down is a leading order structure, but you can try to add corrections to it, perturbative corrections. And basically, Samir Mathur in his argument has sort of proved a theorem which says that no matter, you can correct the state up to all orders, and still it won't matter. It will not change the result. The result will still remain the same. Okay. So this
Sorry,
is
what is this correction to this state look like?
So we are keeping the background completely constant, right? And we are allowing no gravity corrections to this, not even perturbative. I'm not even allowing. I mean, I can allow gravitons really, but I can keep gravitons. I can arrange such that graviton contribution is much less than the contribution of the fields. And then you will see that fields are just going over a smooth background. But then I can start adding graviton corrections. And these corrections, you can hope that these are gravity corrections. These are genuine gravity corrections. So something might change here. But it's proved that it doesn't change anything. The result still remains true, that you have a large entropy after a black hole has evaporated away, assuming that revenants don't exist. Okay. I'll stop for like 2 minutes for questions.
Right.
Yes.
So when you say like graviton corrections, like in 2D, there is no propagating graviton. So
in 2D, yeah.
Yeah, so in 2D, these corrections won't appear, or like they appear in some other way, or
in 2D there's things called boundary gravitons. So you can still correct those. You can take
so they will give corrections to these states.
They do, but
they
won't help. Yeah.
Okay. Sure. Yeah. Thanks.
Now the only thing that we haven't thought about, and I think which was completely overlooked by a lot of people, was that there could be gravitational instanton corrections, in the sense that not just 1 over G Newton kind of effects, they are e to the power minus 1 over G Newton effects. Okay, so when you do perturbation theory, you do perturbation theory in G Newton, but there could be effects, there could be some non-perturbative correction which is of the order e to the power minus 1 over G Newton. And till now, we never really didn't know how to take these effects into account in a gravitational path integral, but the whole discovery seems to be just that now we know how to understand non-perturbative gravitational correction. So this state is really corrected, but it's corrected by non-perturbative corrections. So what has been proved, I was talking about earlier, is that perturbative corrections don't help. Perturbative corrections don't change this result, but somehow non-perturbative corrections do help. And hopefully,
I have a question.
Yes.
Yeah, so do you mean to say that these recent things about ADS2 information loss can be thought of as instant-on corrections, gravitational instant-on corrections?
These things, I mean, they are calling it replica wormholes, but these are really gravitational instant-ons. I mean, these are really corrections in the Rene entropy computation, but these are like instant-on corrections.
Okay, at some point, would you explain this? Maybe need not be now, but like, could you explain more in what sense?
Yeah. I think I think it should be one of the final lectures.
Okay, thank you.
Where I come there. Okay, so this is a naive argument. I've shown you that this is a problem, that you have a radiation at the end which has some non-zero and large entropy, and there is no black hole, so it's not entangled with anything. So if it's not entangled with anything, and if it has a non-zero large positive entropy, that means the state has to be mixed, and that is a tension with unitarity. So unitarity can never do this. Unitarity can a unitary theory won't take a mixed state, a pure state to mixed state, but gravity seems to be doing that. So so I've already discussed.
I have a question.
Yes.
Yeah. So if you look at this pair production happening at horizon as some operation which is just happening locally at the horizon, right?
Yeah.
But
as the time, okay, yes, go ahead. Sorry.
But as the time is evolving, the entanglement seems to be increasing across the horizon.
Yes.
I mean, so, but purely quantum information theoretically speaking, something happening locally cannot increase entanglement, right? Isn't that one of the axioms of entanglement for any entanglement measure? I don't know if my question is clear. Whether it makes sense.
I actually didn't understand the question. I mean, what do you mean by locally?
For instance, local unitary operations cannot increase entanglement, right?
Oh, but the thing is, you know, I mean, see, if you take a system, and if you have a local, okay, what? So we should define what means by local more carefully. So let's say local means either 4-body or 5-body interaction. So let's say you have Hamiltonians, which only introduce interactions across neighboring sites or neighboring few sites. Okay. And then if you divide the subsystem only in those sites, then you can say that Hamiltonian is only interacting in these 4 or 5 sites. Hence, if you only focus on that local system, it won't. So let me just maybe draw something here. So if you have some system A, and if you have some system B, and then you have some HA and HB, okay, and then if you compute the entire, and let's say they are factorized in the sense these A and B are 2 separate Hilbert spaces, and HA is only supported in A and HB is only supported in B. Now if I consider so this is a local unitary in the sense e to the power minus I H A T is a local unitary, and this can't ever change the entanglement entropy of A. And similarly, there'll be a local unitary which is e to the power IHBT, and this cannot ever change the entanglement entropy of system B. But you could just consider that I mean your subsystem could look something like this, okay, which is basically the bigger box. Is it visible? So your subsystem could be bigger box, and the whole subsystem could have the Hamiltonian as HA plus HB plus some sort of H interaction AB. Okay. Then now if I just only focus on A, you will see that it will increase the entanglement entropy. So basically what I'm saying is across the horizon, if I'm dividing the system across the horizon, so it's not local on either side of the horizon, you see. But if I take a neighborhood, maybe a slightly large neighborhood, you will probably can approximate it by some local unitary. Is that
could you repeat your last point again?
I'm saying that across the horizon, I'm dividing the system across the horizon, okay. Then the gravity evolution cannot be thought of as local unitary either in the interior or exterior. It's necessarily the interaction is, there is necessarily an interaction across the horizon. Okay, so it's not, so it's not local unitary. That's the short answer. Okay, I mean you can think of this A and B systems as being interior and exterior, and I'm just saying that there exists this term. This term is necessarily there. Okay. So now, so what we have seen.
I think we have 2 questions. First, Karan, go ahead.
Yeah, just a quick return to what you said earlier about perturbative corrections. I'm a little confused about that. I mean, when we introduce perturbative corrections, don't we? So the setup we have right now is that there's like Minkowski in the past and Minkowski in the future. I collapse a shell and that becomes radiation, but this is like some mixed state in the Minkowski background, right? So now when you say, hello, can you hear me?
Yes, yes, yes.
Yeah, so if you take perturbative corrections, I don't see how the statement of assuming maximally entangled pairs can be taken to be true within that context. I mean, you're assuming that there are these maximally entangled pairs and they give you this mixed state later on.
Yeah.
But if you take perturbative corrections, you should generally change the background geometry. And I mean, even though you end up with a mixed state in the end, it can't be a mixed state on Minkowski. So how does this, I mean, what's the,
No,
I mean, is
okay,
it pinned down that perturbative corrections really don't do anything? I mean, that's the question I'm asking, basically.
I think so. I think it's more or less shown that perturbative corrections.
But you got my question, right? I mean, in the
I
end,
know,
you have
but
a background which is a little deformed from that of Minkowski. And I mean, in what sense are they saying that is, I mean, you can easily say that that mixed state is actually entangled with the perturbed background in some sense, right? And it's pure. So, I mean, why is that ruled out?
Yeah, maybe, okay. So, I mean, I'll certainly come to a point where I'll show that.
Could you explain the question once more, please?
Yeah, you want me to repeat the question?
Yeah, maybe. Yeah.
Yeah.
Maybe.
So the setup that he has right now is that there's, so think of a shell of a null shell, which I collapse, and then this gives me some radiation. I just have like light-like radiation in the end, the simplest setup. And so I went from a pure state to a mixed state, and this whole thing is in Minkowski. And the assumption that he's making is that the pairs that are produced at every step are maximally entangled. Now, the argument is that when you take order G corrections, this does not qualitatively change the answer. But I think if you take gravitational corrections, you change the state from Minkowski to something else. So yes, in the end, you have like this mixed state, but it's not a mixed state on a Minkowski background anymore. Technically, there is a small gravitational correction to the background. And I wanted to know what's the argument that there is no entanglement between the mixed state that you have here and this slightly deformed flat space-time. I mean, why couldn't that be a purification of the radiation? That's what I'm asking.
I guess the argument is if it's a small correction, it cannot purify such a huge entropy, such a linearly growing huge entropy. I mean, if you really look at how large the evaporation time is very large. By that time, the accumulated entropy is too huge. So it can't just be cured by some small corrections.
Yeah, but the whole argument that you were making, just a very quick comment, is like the entanglement is sort of fixed. It's just scaling with n, right? As it's scaling in time, that is the n. So it's large because of the degrees of freedom. So you would again have n into gn or something like that. So anyway, I mean, I'll talk about this later. It's not okay.
Can I say something? Like,
Akhil, actually, Prashant had his hand raised for something.
Okay, go on. Okay, go on. Sure.
Adwait, can you go back to your previous slide where you had that picture of the black hole?
Yes.
Yeah. So I have a very basic question about the setup. So when you say that your black hole is evaporating, do you mean that you already have a fixed background where the slicing, I mean the Penrose diagram is fixed and also the slicing is given, and this already tells you that the black hole is evaporating, and on that you are so therefore psi m has some evolution, but you're assuming that that is given, and then you're assuming that there is some pair creation that's happening, and that the Hilbert space of this new pairs that are created are completely decoupled from this evolution of the background.
Yes. So psi m will have some evolution. Something inside will. I mean, there might be some sort of interaction between particles which are falling in with matter, because eventually that is the reason the black hole evaporates away. But because we are dividing the system across the horizon, we don't really care what's happening in there. We just care about what is the entanglement across the horizon.
Yeah, I was just thinking if you need some actual, I mean, if you actually need, would you not need some information about psi m's evolution to say that okay, the black hole is actually evaporating and therefore there could be some I don't know,
I mean,
entanglement entropy.
I might need it, but I'm just saying that the problem I'm trying to understand is what is the entanglement entropy of the radiation with everything else.
Okay.
So for that question, I don't think it's important about how psi m interacts or how what is the evolution of that particular part.
Okay.
Okay.
Yeah, hi. Can I come back to the comment I want to make? So was Karan asking whether the emitted gravitons and the external radiation is entangled and hence that can change something? Or was that the question?
My question was that the emitted gravitons itself has a coherent state which will change it to some curved background, and your principle of saying that it's maximally entangled would be false because you have to add those dots which he mentioned earlier.
Yeah.
So he wrote that this is approximately, so it's not exactly maximally entangled. So the radiation that you get in the end could have some entanglement with Gn, which is also scaled with n, and this could provide some kind of purification. I mean, I don't see why that is ruled out.
The radiation can be entangled with the gravitons, or what is
with this coherent.
Sorry, just to interrupt. I mean, since it has already been decided that this question is better discussed over Slack, so perhaps Karan can write this question down on Slack, and all of you can discuss it there.
Yeah. So can I make a quick? I just want to confirm it. So I thought
Akhil, you can confirm it from the Slack itself.
Okay, sure. Go on,
right?
go on.
So Adwait, please continue.
Yeah. Thanks. So okay, now okay, what I have shown naively is that it seems that the black hole formation and evaporation has a sort of tension with unitarity. Okay, it seems that gravity is doing something non-unitary because it started with a pure collapsing state, but we ended with radiation, which seems to be in a mixed state. Okay, so let's look at what if I just assume. Let's assume that gravity is unitary. Let's assume that it's an ordinary quantum system, and try to see how the entanglement entropy of the radiation should look like. Okay, so this is the point where we are assuming unitarity, and then we see what I expect. Okay, so generally black hole states are very complicated scrambled states, and such states are given by you can just take an initial state, okay, which is slightly arbitrary, and then you can put a random unitary on it. Okay, so what I've done is I've taken an initial state which is also of the system black hole plus radiation. So B and R means black hole plus radiation. So it's a state of black hole plus radiation, and I'm applying that some initial state by some random unitary operator. This is supposed to mimic different kinds of time evolutions, and that prepares a final black hole state for me, final black hole plus radiation state for me. Okay, and this is an approximation because we're just assuming that black holes evolve completely randomly. They're so chaotic that you can just use a random unitary to describe the evolution of the state, and it's just one shot. You don't have to put in time in there, because I mean, if you create a complicated enough unitary, it can simulate a long time evolution of slightly complicated unitary. So you take this state and assume that this is what a black hole state looks like, and then just compute a density matrix. So the density matrix is of the whole system is this, and then you can compute a reduced density matrix of only the radiation system. Okay, and that object is going to be a function of the U that we used here. Okay, and that object will look like, you trace over all the black hole parts of the states, and just trace out that from your original density matrix. Now at this point, even though I'm calling these systems as black hole and radiation, you don't really have to think about it that way. You just think these as two systems, two quantum mechanical systems interacting with each other. Okay, with under some unitary evolution. So I can find out reduced density matrix of the radiation of one of the system. This is the same, and then let's compute the fine-grained entropy of this object. So it's rho r, which is also a function of U, and that fine-grained object will be just basically von Neumann entropy of your reduced density matrix. Okay, but now
Adwait?
Yes.
Sorry to interrupt. I just had a quick question. So when you said that the state has to be purified for things to make sense, it seemed like you wanted one effect that did the entire process. Is it not possible that you could have multiple small effects that sort of cumulatively purify the entire thing?
So let me just tell you what is going to happen next. Right now, what I've shown is that the contradiction only happens after black hole has evaporated away. Okay, you see the contradiction is towards the very end. Now I'm going towards improving this paradox, and I'll show that there is you don't even have to go to the end of the evolution. It's basically the problem of the black hole information starts literally at the midpoint of the evolution. Okay, well, it's called the midpoint. It's not the literal midpoint, but that's where I'm going. So I'm just improving the contradiction now to show that all the things that you were thinking about, that at the end we go very close to the singularity and all, it won't matter, because the contradiction starts way earlier than the late time. Okay,
I see. Okay.
So now we have this is the fine grained entropy of the reduced density matrix of the radiation. And what I really want to do is that I really want to find an averaged number. Okay, so if I average this under all the unitary operators, okay, and this is some Haar measure. So I'm taking a Haar measure and I'm averaging the von Neumann entropy with this, and then I get some averaged quantity which I have written here. Okay, so this is some average quantity that I get. Now I'm going to write down an answer. I'm not going to explain how this answer comes because it's available at in a lot of standard texts. This answer, if you assume that, so first of all, what you have to assume that the Hilbert space of the black hole system is much greater than 1, and Hilbert space of the radiation system is also much greater than 1. Okay, so both of them are very large Hilbert spaces. In this limit, what happens is the answer to this question, this object here, looks like this. And let me just write down the answer. So it's log of dimension of the radiation system minus dimension of the radiation system divided by twice the dimension of the black hole system, plus some further corrections in 1 upon dimension of the black hole. And this is the answer when dimension of the radiation is less than dimension of the black hole. Okay, now there's a second answer when this condition is inverted, when dimension of the black hole is less than dimension of the radiation. What happens is you get this answer. Okay, and it just the formula just flips. Okay, so this is the answer. What is this telling you? That if I just assume a unitary evolution, and if I just assume that there are two systems, two quantum mechanical systems interacting with each other, and their Hilbert spaces are large, then on an average the entanglement entropy of any one of the system. Now, because I am assuming unitarity, if I compute entanglement of the bar of the black hole or radiation, it's going to be the same. So this is the same as fine grained entropy of rho black hole with that particular unitary. Okay, it's going to be exact same answer. But what it tells you, that number, the fine grained entropy of either of the system, is almost always follows the log of the minimum, log of the lower dimension object. Okay, so when dimension of the radiation system is lower, the answer is the dimension of the log of the dimension of the radiation. And then these are some corrections which you can ignore when these ratios are different. And then when black hole dimension is less, you have this answer. Okay, okay, so now let me try to just draw what this graph looks like. Okay, so now let's draw this. So let's draw two diagrams. And first of all, what we showed, and let's say this is n or time, whatever you want to call it. Okay, And here I'm going to draw two graphs. So first, let me draw a graph of entanglement entropy, the coarse grain entropy of the black hole. So now, as we said, that the coarse grain entropy of the black hole is proportional to its area.
Can I ask something?
Yes.
So when you did that calculation, was it also done using some replicas and so on, or
No. It's a very crude statement. It's not a very precise.
Or is it so? Is it like two saddles, or like how does that come out? Like there are, I'm guessing saddles because there are two options depending on some parameter.
Probably, yeah. Yeah, I don't want to go into it because it's just a result that you have to use. That's it. It's
okay.
But
Okay.
maybe I'll put the derivation in the Slack.
No, the reason I asked is because it's entropy. I would have guessed it's like a replica thing, and then all these recent developments are talking about how there are two leading replica contributions.
The thing is, I have seen multiple derivations of this, not just using Haar measure, doing a lot of different things. So there's no one single derivation. So I mean, I think what you're asking for a physical principle to understand this result. So I have not really understood.
Yeah, I was just wondering, because all these recent developments are about how two different replica contributions are relevant for late and early times. I was just wondering if the way that is derived also can be reconciled with the.
I'm not sure.
Right? Okay.
I'm not
thanks.
sure. I'll try to tell you.
Okay.
Find it. So first of all, let's just look at the coarse grained entropy of the black hole. Okay. Now, coarse grained of the entropy of the black hole is mostly dominated by its area. Okay. Because the area piece comes with 1/g Newton, and then there is a S bulk piece, but S bulk piece is always subleading. Okay. So it's mostly dominated by its area term. And then when you see coarse grained entropy of the black hole, you'll see that the coarse grained entropy of the black hole just slowly decreases and goes to 0. Okay. That's because black hole just evaporates away. And coarse grained entropy generally is a measure of degrees of freedom. So if black hole evaporates away, that means there are no degrees of freedom of black holes. So at some late time, you'll see basically that the coarse grained entropy of the black hole should go to 0. Okay. This is just an argument. The curve is also qualitative. I'm not drawing exact curves. And now let's take and let's draw the result that we had drawn. Is that it's a fine grained entropy of the you could call it radiation or black hole also. This is a fine grained entropy of the black hole, or let's say radiation. That's what we computed. So let's call it radiation. Okay. Now these are the two systems which are exchanging degrees of freedom between them. And what Page told us is that roughly it should always follow the minimum of both of them. The final answer of either of the system, it doesn't matter which system you are looking at, of either answer, the fine grained entropy should always follow the minima of the log of Hilbert space of both of them. Okay. Hence, what Page says, according to Page, if you follow that formula, what Page says is that the curve of the entanglement entropy should really look like this. It should start from here because this is the minimum of the two curves, but at this point it should turn back down and it should go back to 0 here. Okay, because that's what Page told us, that the entanglement entropy of either of the system only follows the minimum log, the minimum Hilbert space log. Okay. Just one sort of cheating I have done is that I have the yellow line is really a coarse grained entropy and not a fine grained entropy. Okay. So, but the point is, fine grained entropies are always lower than coarse grained entropies. So it's sort of an upper bound. But the point I'm trying to tell you now is that you don't have a contradiction towards the end of the evaporation. You have a contradiction here itself. Okay, this is the point where the fine grained entropy. So let's say unitarity is we have let's say gravity has unitarity. What does that mean? That means that the fine grained entropy of the radiation should be exactly equal to the fine grain entropy of the black hole. Okay, but we also know that the coarse grain entropy of the black hole is always greater or equal to fine grain entropy of the black hole. Okay, what does that tell us? That tells us that, so I just so that just tells us that where is the contradiction? The contradiction is basically that the fine grain entropy of the radiation should always be less than equal to the coarse grain entropy of the black hole. I'll explain this again if it's not understood, but it's just true from the expressions.
Adwait?
Yes.
Like, did you tell us like why Page told us this to take the minimum, or like are we to accept this as something he told us?
This is just a result from unitarity, right? What we did was we assumed this unitary operator acting on some initial state,
okay.
And then we created these states. From these states, we created the reduced density matrices, and then we computed average over the Haar ensemble of those entanglement entropies. Okay. And then the result is given by this. So Page's result is basically what follows from unitarity. What unitarity
I see. So this tells that we should take the minimum of those curves, is it?
Exactly. So unitarity tells you that you should take the minimum. And then if you actually plot it, you'll see that the ever-growing entropy has a problem right at this point. At a point when the black hole entropy, coarse grain entropy really becomes equal to the entanglement entropy of the radiation.
Okay.
This is a tricky point to understand, and I'll wait for some time if people haven't understood. People have more questions. So,
but basically, you get this as a result by your computation in the last slide that you take the minimum. Is that correct?
But but the thing is, this is a different approach in the sense there's no real reason to assume. There was no real reason to assume that gravity is unitary. You could have just concluded that gravity is non-unitary.
Yeah, that's all right.
This is coming from a different angle, saying that I'll assume unitarity and then I'll see what is the problem.
Sure. Okay.
Adwait, can you explain like where the problem is actually, like why I have not understood properly why that.
See, this is the curve that we drew, right? This is the curve that we derived. This is the n log 2 kind of result.
Right.
That is just growing. It's a fine grain entropy of the radiation. And then, so the fine grain entropy of the radiation, according to unitarity, also has to be fine grain entropy of the black hole. Okay. Because they're just complementary to each other, and we are assuming that it's a pure state across. So by unitarity, fine grain entropy of the radiation should be equal to fine grain entropy of the black hole. And we also know that the coarse grain entropy of the black hole should always be an upper bound on the fine grain entropy of the black hole. Okay. Now we just put these two equations together, and it'll tell you that the fine grain entropy of the radiation should always be less than equal to coarse grain entropy of the black hole.
Okay.
And that contradiction happens here because you see this white curve is really the fine grain entropy.
Okay.
And this yellow curve is really the coarse grain entropy. So the later part of this beyond this red dashed line, you have a contradiction with unitarity.
I think Rohit had a question.
Yes, please.
Feels like we are comparing the numbers of apples and numbers of oranges because of this conflict at this point.
What are apples and what are oranges?
What I mean is like, see, fine grain entropy and coarse grain entropy, they are like two different things.
But one is bounded by the other.
Yeah, true. But the two bounds are different. Like one is the coarse grain for black hole, and the other one is coarse grain for radiation. So it's like we are only we are only talking about the number stuff rather than how we are computing it.
Please say that again.
Okay, anyway.
No, I haven't understood the question, please.
Okay, so what I mean is, see,
the inequality that is between the coarse grain entropy of the black hole and the coarse grain fine grain entropy of the black hole itself. And we have one condition that is due to unitarity, that the fine grain, the black hole and the radiation should be same. And when we are, so these are the two different kind of equations. I mean, not in the exact same class, what I mean. I don't know whether I'm saying it right or not, but it kind of feels like we are counting. Anyway, I'll leave it to you.
Okay, let me explain this again. Is that if you assume unitarity, the fine grain entropy of the radiation is equal to the fine grain entropy of the black hole. Okay, but the fine grain entropy of the black hole is always less than the coarse grain entropy of the black hole, right? Hence, the fine grain entropy of the radiation can never be has to be less than coarse grain entropy of the black hole. Or let me say that let me put it the other way. It cannot ever be greater than equal to the coarse grain entropy of the black hole. Does it make sound good?
Yeah,
the
yeah.
Fine grain entropy of the radiation can never exceed the coarse grain entropy of the black hole. Think of it this way. Let's say black holes have some degrees of freedom, okay, and radiation has some degrees of freedom, and then they are entangled with each other. After some point, we are saying that the entanglement entropy of the radiation has grown so much that black hole doesn't even have those many degrees of freedom to accommodate for that, right? If
so this puts like a bound on it.
It puts a bound on it, but it also shows a contradiction that it also shows that the computation that we did is contradictory to unitarity. And it's not contradictory to unitarity when black hole has evaporated away. It shows that the contradiction is right in the middle, when the basically coarse grain entropies of both the systems become same. That is a point when
yeah. Thank you.
Is it me or is?
I can see Adwait in the participants list. I think his internet connection is probably bad or something. Is there anyone in the participant list who is in TIFR right now? Ah, Adwait is back.
it's me who went out.
Yeah, Adwait, you got disconnected. So.
Yeah.
Adwait?
Hello, am I audible?
You're audible now, but we can't see your iPad screen, and your connection is showing that it's a bit poor.
Okay. Is it okay? It's visible now, right?
Yeah, you're good to go.
Okay. Yeah, I really want to I really want you to take this point home, that there is a real contradiction here, and it's not at very late times, but it's towards in the middle of the black hole evaporation. And if you have any questions, please do ask.
If you don't mind, can you summarize what happened in the previous slide? Like, what was the precise computation?
What is the precise computation?
Just summary, especially the last two lines.
These last two lines?
Yeah.
See, what we are doing is we are
Sorry,
assuming...
I cannot hear what Subbu was saying. I couldn't hear the comment.
Subbu wanted to explain the last two lines of the present slide.
Yeah.
Oh, okay, this is much better. Thanks.
Yeah. Okay, so let me explain this slide again. That what are we doing? I want to assume unitarity, and I want to assume and I want to see what happens to the fine grain entropy of either of the two systems. Okay, so I'm considering a system of a black hole plus radiation. Let me take some initial slice, whatever initial state, whatever state I choose. Let it be entangled between B and R system, the black hole and radiation system, and let's put some apply some unitary on it. Okay, this unitary is just a random unitary. I'm just trying to see what happens if I randomly evolve a state by a unitary operator. Okay, so I'm evolving this state by U, and whatever state I get, I call it my final state. So this psi BR on the left hand side is my final state of the black hole plus radiation. Then you can find out the reduced density matrix of only the you can do it both ways. You can find out the reduced radiation for reduced density matrix for radiation or black hole. Once you find that reduced density matrix, you can compute the fine-grained entanglement entropy, which is just von Neumann interval entropy. But all of this is still a function of this unitary that we used, and we really wanted an averaged answer. So we average over all possible unitaries by using some Haar measure.
So after you averaged, is it still the fine-grained entropy, or is it?
Is it still the fine-grained entropy?
How should I think of it? Because in the next slide, like you told us that this leads us to conclude that one part is like that this result tells us to take like fine-grained entropy in one part and coarse-grained entropy in the other part, right?
Yes.
So like how should I interpret this LHS?
You should think of this as being on an average, this being true. So these, whatever the fluctuations are to this result, whatever the ensemble fluctuations are. I mean, if I take one U1, a particular unitary, and if I take second unitary, the difference between them, difference between those two page curves, or difference between those two curves of the entanglement entropy will go down as you increase the dimensions of your of the Hilbert spaces of both systems.
But it is still the fine-grained entropy, right?
It is still, I mean, it's averaged version of the fine-grained entropy.
Okay.
But it's you could, if I can show that I get an averaged quantity, and if I can show that the fluctuations around that average quantity are very small, then basically I'm making a statement about the quantity itself in that limit. And in that sense, Page's result can be directly assumed to be true for whatever.
So one line in the answer corresponds to fine-grained entropy of the radiation, and other corresponds to coarse-grained entropy of the black hole. Is that so?
No. So see,
because in the next slide,
both of them are results of fine-grained entropies. Okay.
Yeah.
So it's fine-grained entropy of the radiation is equal to fine-grained entropy of the black hole, and both of them have exactly the same result.
Yeah, but you said in the next slide that this leads us to take the minimum of the two curves.
Yeah.
So like, how does that happen?
I'm just saying I don't know how to compute a fine-grained entropy of the black hole. Okay. I don't know how to compute it, but I know what is a coarse-grained entropy of the black hole, and because it's just proportional to area.
Okay.
And coarse-grained entropy really bounds the fine-grained entropy, which is this statement. Okay. So the first statement is just unitarity, but I can't compute the right-hand side of the first statement because I don't know how to compute fine-grained entropy of the black hole. But I know that it's bounded by the coarse-grained entropy. Hence, it leads to this equation. That if this is true, then it's basically saying that if the coarse-grained entropy is an upper bound for the fine-grained entropy of the black hole, it's also an upper bound for the fine-grained entropy of the radiation.
Right.
And that's the result.
Okay, great. Yeah. Okay, thanks.
Prashant has a question.
Yes. So it's a very basic question. So in this curve, the yellow line is an average quantity, right? So
yellow line is just the area of the black hole which is evaporating away. So it's the coarse-grained entropy.
Okay, sorry. Again, so in this, which one is the average? The white line is the fine-grained entropy is the average.
No. Average. See, the average result is just a trick to understand what happens when two systems interact unitarily. Okay. So this is the average result. What is this result telling you? This result is telling you that if two systems are interacting and they are also exchanging degrees of freedom, in the sense their Hilbert spaces are changing, then as time goes on, if I compute entanglement entropy, the fine-grained version of the entanglement entropy for either of the system, it has to follow this thing. So let's say we start with radiation system being small, which is the early stage of evaporation, and black hole system to be large, having large Hilbert space. Okay. Then at the initial times, what it's basically saying that the entanglement entropy should look like log of the dimension of the radiation system. But later on, at a point when the black hole is decreasing, it's evaporating away, and the radiation is growing, at some point this exchange will happen, that the radiation Hilbert space of the radiation system will become bigger than the Hilbert space of the black hole system. And at that point, you should start following the log of the dimension of the black hole system as your answer for the fine-grained entropy.
Okay, so in the next slide, you have three different things. You computed the coarse-grained entropy of the black hole, is this area, which you got from like the first law, second law, whatever. And then you computed the fine-grained entropy of the radiation, which you did earlier today. And then you're saying the which curve you should track is given by this previous slide. That's what.
Yeah, exactly. What should be the unitary answer is given by the previous thing. The thing is, you see, okay, let me draw another. So the we know at t equals to 0, this, let's say this is the coarse-grained entropy of the black hole, or let's say I also know that this is the fine. Okay, the fact that coarse-grained entropy bounds the fine-grained entropy tells me that if I could draw the fine-grained entropy curve of the black hole, it has to go something like this, right? The blue curve, this is a imaginary situation. I can't.
Adwait, I don't think anyone can see the blue curve. Maybe use a brighter color.
I don't know what color to use really.
Use green, light green.
Okay.
Actually, whichever color you choose from the bottom rows.
Oh, I see.
Yeah, use the brighter ones.
Okay. So let's say I'm drawing now an imaginary curve, which I don't know how to compute, but I'm drawing now a fine-grained entropy of the black hole, and it should look something like this. Because, and let's say this is what a fine-grained entropy of the black hole looks like. Let's say, I'm not saying this is it, but let's say. So it always has to be lower than the yellow curve. That's the point. Okay. But I don't know how to compute the green curve. So I'm assuming that the maximum that green curve, the tallest that green curve become is the yellow curve. So yellow curve is just an upper bound for all possible green curves. Okay.
Okay, we have a question from Deepangshu.
Yes, please. It seems like the more I'm answering, the more people are getting confused. Anyway, yeah, Deepangshu, please.
Hi. So actually, I mean, I was fine till you drew the green curve. So my first question is, qualitatively, can you claim that, I know you can't compute SF black hole, but can you at least say that it's monotonically decreasing always?
Yeah.
This is my first question. Second is, isn't it true that S coarse-grained black hole is basically S fine-grained black hole plus order G Newton correction? Because, I mean, the point is that you drew the green curve as having completely non-perturbative corrections to the yellow one, at least from the picture. But shouldn't it just be order G Newton different?
Well, you could.
I mean, I'm supporting
you have to add all perturbative and non-perturbative corrections. See, okay. First of all, why do you know that curve monotonically decreases? It's because
Deepangshu, I think we are getting a feedback from your end.
Hello.
Yeah.
Yeah, so, go ahead.
First of all, why does the fine-grained entropy monotonically decreases? Because we know that the black hole evaporates away. Okay, there's no black hole at the end, so there's no Hilbert space of the black hole at the end. Hence, the fine-grained entropy also is 0. So it has to decrease. But whatever it decreases, so it has to start from t equals to 0 value, and it has to end at 0. But it has to be bounded by yellow curve. That's the argument. It cannot be like, for example, there's no way that the curve can go like this. It can't do this. It cannot be above the yellow curve. It always has to be below the yellow curve.
Okay, I think Arunno has a question, and I would like to tell Adwait that after this question answer, I think I will give you 5 more minutes to wrap up.
Okay, so Adwait, I have a question about, so as far as I understand, the thing we are looking for, or the goal would be to find a way to calculate the fine-grained entropy for the black hole.
Yes.
And as you said, this should also be the fine-grained entropy for the radiation.
Yes.
So this shouldn't ideally be always monotonically decreasing, right? At some point, it should change and be monotonically decreasing, the fine-grained one as well. Before that,
so the fine-grained one should always follow the red curve. That's what Page told us.
Okay.
So even the black hole entropy, initially it should look like it's increasing.
Yes.
And after page time, it should look like it's decreasing.
Yeah. Right. Thanks.
Okay. Yeah, even though I just have 5 minutes, I still sort of have a feel that maybe okay, how do I get a feedback from people if I have to ask that whether people have understood this?
People can press the yes button beside the raise hand button.
Guys, please, if you have. Okay.
You can also press no if they have not understood.
Just press no if you have not understood. Okay.
Yeah, I think at some point we had 21 yeses and so far 1 no, and I think we should just continue.
Okay, all right. Maybe okay. So this is now. I just want to. Should I make this argument or not? Let's see. So whatever I said is basically whatever I said is really just is not. I mean, one more thing I want to tell you. Maybe I'll just say it and I'll just draw the graph. The thing is that all the arguments I have said until now about the pages curve and the problem being just after the page curve has really nothing to do with evaporation. Okay, as long as I can show that the connector sections stretch across horizon, which also happens in eternal black hole. Even eternal black hole pair produce, and even eternal black holes radiate. But the point is, eternal black holes are also absorbing radiation at the same time. So they remain in equilibrium with the radiation, so they evaporate and absorb the radiation at the same rate, and hence it remains the same size. But the problem of pair creation and the ever-growing entropy beyond the page time still exists in the eternal black hole. So let me try to draw the graph for the eternal black hole, and it's a simpler one. So again, we are drawing entanglement entropy, fine-grained entropy. Okay, again, let's say the horizontal axis is time, and the entropy of the black hole just remains constant, the coarse-grained entropy, right? Because the area of the black hole, of an eternal black hole, is always whatever it is. So it is just here. This is entropy.
Adwait, use some brighter color than the red.
Sorry. So you just have this coarse grain entropy of the black hole, and it always remains constant, whatever it is. Okay, for all times, because it's an evaporating, it's a eternal black hole. And what the result we showed, that the pairs keep on producing, also keeps on happening in eternal black hole, because the connector region always keeps on stretching up. So the n log 2 result is still valid. So you'll see that the n log 2 result is still valid here. This is the fine-grained entropy of the radiation, which approximately goes as n log 2. Okay, and you can again see that the same contradiction happens at this point. And this point is what I'll call the page time. Okay, So if I have to tell you that what is the curve that what is the curve that page suggests here, it basically says that initially the white curve is the lower curve, so it follows this, and after this point it starts following the lower curve here. And again, there is a contradiction beyond this point, because the contradiction is that the fine-grained entropy of the radiation seems to be bigger than coarse-grained entropy of the black hole, okay, which is a problem, which is not allowed. Is this clear? That the paradox which I have shown you before in evaporating black hole. So what the only difference is the coarse-grained entropy of the evaporating black hole kept on decreasing. It just went to 0. But here it's not going to 0, it's remaining constant. But the problem is still there, because at some point you'll see, at some point in time, you'll always see that the fine-grained entropy of the radiation will cross the coarse-grained entropy of the black hole, which is a problem. So I think I'll stop here. If you have any more questions,
I think Karan had his hand raised. Maybe Karan can go ahead first.
No, I had a question, but then I think that was answered through another discussion. So that's
okay, then Prashant, go ahead.
Yeah, so I have a related question to earlier. So here again, what you're saying is that you are taking, I mean, in this n log 2 when you're writing.
Yes.
There is enough radiation that, I mean, can you actually treat it perturbatively with the background geometry fixed? Is this a good thing to do? Or is this even sensible to do? Because if you're sending out enough packets such that this is happening, whatever radiation, then like, can you actually assume that the background geometry is fixed and make this argument?
I see. I'll give you an argument for this later. But basically, as long as so if you look at it in action, you'll see that the leading order piece comes at 1 over G Newton. The next leading order piece, the subleading order piece is order 1. Let's say the gravitons come at order 1, and if you just add free scalar field, it will also come at order 1. So if you just look at the action, you will have a 1 over G Newton piece, and you will have an order 1 piece, which is a graviton action and which is a free scalar field action. But now the trick that we do is we just add large number of scalar fields. So let's say that large number is C. Okay, so we have C scalar fields. So now if you look at the action, what happens is there is a 1 over G Newton contribution of the 0th order background. Then there is an order C contribution from the fields that you have put in. And then there is an order 1 contribution of the gravitons. So as long as C is greater than 1, I can ignore gravitons. So it's perfectly okay to keep the background fixed and ignore the gravitons. It still somehow remains in the probe approximation as long as it's not order 1 over G Newton. So C has to be much less than 1 over G Newton, but it has to be much larger than order 1, so that I can ignore gravitons. I'll describe this in.
No, that makes sense. But the point is, because of this order C term, should that not be treated in the field equations itself directly then? Like even if you assume that there's no.
It should be. Yeah, it should be.
Yeah. So
but it won't back react.
How? Why? How can you say that? Because what I'm saying is the graviton is that you are solving still. I mean, when you say graviton, you're solving linearized Einstein equations or something, right?
Yes.
But if you have these many scalar fields or whatever, this much energy, shouldn't you actually be solving non-vacuum Einstein equations and seeing that the background actually changes?
I see.
This is related to my earlier question also. When you drew the other diagram, I had the same.
Yeah. Right. And okay, I'll just try. Can I just say one short thing?
Just let me. Sure. Go ahead.
Yeah, I think this is also related to what I was bringing up last time as well. So I mean, if you have like these corrections which are creeping up, then I mean, in some sense, you're taking this to not be a flat space-time at late times. I think that is maybe some subtlety here, which is not. I mean, yeah.
Yeah. Go ahead. I'm listening to you.
No, that's it. Like, I mean, I think these are related. I mean, there is an argument to be made that order G Newton results become significant at late times, possibly. I don't see why that is why that should be ruled out. I mean, at least I can't see it. I mean, if it exists, I mean, you can just tell us what the
I'll give an argument for this and in later lectures, that how you can exactly rule it out. You can stop it from back reacting. So first of all, let me say that the 2D models and 3D models are quite simple because they just don't back react. There's no coupling of the yeah, the metric always remains fixed. The back reaction is always added to the dilaton in some sense. So I think I have to tell you more details, but I'll give you the mechanism of how you can ignore these things.
Adwait, small comment to make. This C number, I mean, regarding Prashant's question, the C number of scalar fields that you introduced, and you're assuming that C is much less than 1 by G Newton.
Yes.
Doesn't it like also, don't you have to also make assumption about how exactly the scalars are coupled to gravity?
In a model I'll describe, I don't have to do this. You can just say that it's minimally coupled. That's it. All of your questions are good questions, but I'm going to come to that. See, the thing is, first of all, until I introduce the model, I can't make any specific statement because I think it's dimension dependent.
Okay.
It will depend on everything.
Okay.
But once I introduce the model, all of your questions, you can either ask them again or I'll definitely talk about them.
Sure. I think then it's best if we wait and then ask.
Yeah.
Thank you.
We are okay. Maybe one more lecture.
I have a quick question.
Yeah.
So the stage time, where presumably that's where the dimension of the radiation Hilbert space becomes bigger than the dimension of the black hole.
Just a minute. I have to attend to something. Just give me 1 minute. Okay. I'll be
Okay.
back. I'm really sorry for this.
Okay. Sure.
क्या हो रहा है? एक Hello. Yeah. Extremely.
Yeah. Hi. Yeah. No problem. So what I wanted to understand is that so this space time. I mean, this is occurring at some. I mean, this is a point that is dynamically occurring, right? Like, I mean,
Yes.
in the evaporating. So, is there an understanding of at what point in the Penrose diagram this occurs? I mean, in any example.
Let's see. Maybe I've not directly seen it, but maybe. Oh yes, of course. I mean, yeah. Okay. The thing is, to cure this problem, we'll introduce something called an island.
Okay.
And, basically, the answer is not helpful, but these islands are the pieces. When these pieces become relevant, that is exactly the point where the contradiction occurs. So these islands are basically non-perturbative corrections, which become really important at certain points, and those are the points at which you. So yeah, I'll talk about this.
I see. Okay. Thanks.
I think at this point we should just unmute ourselves and thank Adwait for his lectures. I think because we have already 15 minutes over time, let me pause the recording and people can continue the discussions of the record.
Yeah.
Okay, welcome back to the post-lunch session. Parthiv will continue to tell us about S-matrix Bootstrap. So over to you, Parthiv.
Okay, so just a brief recap, we did not do anything really yesterday. So today we start with the actual stuff. So let me just, this is the S is the S matrix here, and tau is the so-called transform matrix whose elements we are interested in. So we are interested in whatever the property that we study of this TST, and this will be the center of our investigation from today onwards. By the way, we are always in the center of mass frame, so these conditions are there that we'll be doing. Okay, so
quick question.
Let's go to the next slide. Fine. Okay.
A quick question. Are we only going to look at 2-2 scattering, or
any question?
are we
Yes,
only
yes,
going to
2-2 scattering?
Okay,
Yes, only
okay.
2-2 scattering. Only 2-2 scattering. Okay, so the partial wave expansion is a very is a common tool in the non-relativistic quantum mechanical scattering. So we can also do the same thing in the relativistic scattering, relativistic scattering scenario. So the idea is that it would be good while the momentum eigenstates that we've been talking about are really a continuum basis. So it would be ideally good to have a discrete basis. So in this case also we have such a discrete basis. So suppose because if we are in center of mass frame, so suppose just look at any two particle state with center of mass state. Of course, this is this E is simply related to now P1, P2. One can it's very easy to see that the configuration space, that the space resulting out in the momentum space is an S2. So one can consider eigenfunctions on S2, and which are essentially just solution of the Laplace equation on S2. And these Y's are now my partial waves, which are the usual YLM, the usual YLM, like usual spherical harmonics. But only now, there's this, so L and M are they take the usual because S2 is compact. S2 is discrete spectrum. I mean, in general, it will have a discrete spectrum, and we will have a set, a basis of sets, which will have a total energy E, a total momentum P, which is in this case 0, really.
Sorry,
and lined by.
Yes. I have a question. Yeah. Could you just tell me once again what is this S2?
Yes. Yeah. Oh, S2 is a two sphere. So S2 is a two sphere.
Yeah, but I didn't understand why does those conservations invest?
Yeah, what you do is this, that if you solve this equation, these two equations, like P1 plus P2 equal to 0 and EP1 plus EP2 is equal to E. If you solve this equation, you will find out that this we are in 3 dimension, and of course, we are in 3 plus 1 dimension, so 3 spatial dimension.
Oh, this is just a scattering S2, like this is just the scattering angles that S2, or
no. I mean, you should really,
but then go on. Sorry,
you should really think about this S2 in the momentum configuration space and as scattering S2, and you're right actually. But only, I think most of the cases in non-relativistic quantum mechanics, we think that rotation sphere, rotation symmetry, the configured position space. Here we're just considering in the momentum configuration space, not the position configuration space. So these 5 states, which has 4 labelings. There's a total energy E, there's a total momentum P, and then there's this L, which you can interpret as angular momentum, and M is the usual 3 component of the angular momentum. I mean, it's component of the angular momentum. And now you can also choose to decompose the T matrix in the previous slide, in these bases. And if you do this decomposition and systematically take care of all the normalization and etc., you will get a new expression you will get an expression for an expansion actually you can write an expand, you can reach an expansion for the TST. PL, but then this is cos theta, where cos theta is written, can be expressed in terms of S minus, well, this is really M1 plus M2 whole square if we are considering a scattering of the type A plus B going to A plus B. Now cos theta, theta is an angle, essentially it's a scattering angle. So if you are looking at the center of mass frame, so this is, let's say, A, this is B, and then this is, let's say, goes to A. Sorry, just use some other color.
Parthiv, there is a question from Shubham. Can you just explain the the eigenfunctions of S2 basis once more?
Okay.
As in why?
Yeah. So okay. So the eigen. Yeah. Hello. Yeah.
I think Shubham's question is, why are we choosing eigenfunctions of S2 as a basis?
Oh, okay. I think this is well, we are really choosing a discrete base. We are really searching for a discrete basis, and I think one of the natural way this in this way we are harnessing the rotational symmetry of the problem. So that is one. So that's why from harnessing the rotational symmetry to harness the rotational symmetry, we are using this basis on the like S2 or slash. These are also harmonic functions of SO3. Now, because it's a two-particle composite system, so I won't be able to talk in terms of really individual kind of angular momentum or spin or kind of stuff. But more you can think of this is an orbital angular momentum eigenfunction that we are choosing. But since we are only with scalar particle, we do not have the complication. But had we not have the scalar particle, but suppose some kind of spinning particle, then the so for example, in the partial wave expansion, this L would have been the total angular momentum, where that would have been the addition of the orbital angular momentum and the spin angular momentum. Does this make sense?
Yeah, I mean, I'm just confused. Like, why, I mean, why S2 and not some Lorentzian this thing? Like, are we just looking at Euclidean? Like, I mean, why not H2?
No. S2 has No. S2 has come purely from this constraint. So this P1 plus P2 equal to 0. I mean, it could have been any capital P. So it is this.
Capital P is a vector. Capital P is a vector in Lorentzian signature or Euclidean?
No. Capital P is a vector in Euclidean. So capital P is a spatial momentum.
Okay. Yeah. That's what.
Yeah. Spatial.
That's what I want.
Yeah. Okay. So right. So this angle is basically the scattering angle theta, and this can be expressed in terms of cos theta equal to 1 plus this 2t by s minus this m1 square. Now, when you are considering a plus b to be distinct, there is nothing restriction on L. L can take any integer value, of course. So L can be any integer. Sorry. L can be any integer, non-negative integer value. However, if you choose identical particles, that means if A equal to B in every sense, identical particle, then theta going to pi minus theta is a symmetry. Which clearly shows, I mean, as a consequence of which it is very clear to understand, it is very clear to get that L will be only even. So for identical particle, so L is only even for identical particles. Note that this information only comes after you impose the theta going to pi minus theta as a symmetry of the problem, as a symmetry of the problem when you have identical particles. So theta goes to pi minus theta means basically you are not being able to any distinguish between A and B. So if you interchange A and
yeah, so there is a huge lag from your end, and also your voice is breaking quite frequently over the last 2 minutes.
A and B, you should not be able to distinguish that should not change your
I have a question.
Parthiv,
okay, so
hello?
I think we lost Parthiv.
Okay.
Yeah, I think he is using mobile data. Okay, please go on.
Okay. Okay.
I also had a question to ask. Maybe once we reach the end of the slide, I will ask you.
Yeah. Okay. Sorry, an interruption. Network problems are there. Okay. So yeah, what I was saying is that introducing this this angular momentum basis, I can have this expansion of TEST in terms of this Legendre polynomial, where L is all positive L spans over all positive integers, and cos theta is expressible in terms of this Mandelstam invariance S and T like this way. However, this is so when L is all positive integers, so all non-negative integers, L equal to 0 is also there. This is the case when A and B are distinct. I mean, A and B are distinct. Even like I have chosen A plus B going to A plus B, could have chosen A plus B going to C plus D. Whenever everything is distinct, all partial waves actually contribute. However, if A and B are identical, then there's an extra symmetry, which is theta going to pi minus theta. It's the basically exchange symmetry. And by virtue of this exchange symmetry, it's quite trivial to observe. It's quite trivial to obtain that only even L's will contribute. So thus, for when you are considering identical scalar bosons, you are in the partial wave expansions, only even partial waves will contribute. Okay. So any question?
Yeah, 2 questions.
Yeah.
Why does it look like cos theta is not bounded? I mean, am I just not?
No. Cos theta is obviously bounded. I mean, cos theta it is the physical cos theta. So cos theta is -1 to +1. So it will depend on. So suppose if you fix S, that will constrain the value of T. Okay. The physical T.
S and T are not independent. I thought S is just in. Oh, okay.
No.
Okay,
So what is the
okay,
S
cool.
plus
maybe I'll work it out. That's okay. Second, is this theta goes to pi minus theta some kind of crossing, or is it?
No. It's not crossing. It's the exchange symmetry of identical particles. So basically, when you have A and A. So okay, this is confusing. So let me just do it.
It's just AB exchange, is it? Ingoing AB exchange.
Yes. So when this is all are A, so it really does not matter whether. I mean, you cannot really distinguish whether the particle is coming from the left hand side or the right hand side. or whether the outgoing particle is going towards the upper side or the lower side. So that means that there's an exchange symmetry between pi and theta, theta and pi minus theta.
Is that true also for half integer spin? Like I could just replace theta by pi minus theta?
Okay. Yeah, no. Actually, I think half integer spin, yes, but half integer spin you will have to. It will be anti-symmetry, so it has to take up one minus sign.
Oh, I see. Thank you. Okay.
Parthiv, I have a question about this. How you got this S2? I have not really gotten, because you are telling that P1 plus P2 equal to 0 and EP1 plus EP2 equal to some constant E.
Yes.
How that gives you the sphere S2 as a configuration space?
Okay. So if you, for example, if you break this P1 and P2 in components, like 3 components, so each of them has 3 components.
Right.
And EP1 and EP2 are on-shell energies. So they are, so for example, okay, let me just clear up. So EP1 is simply, EP1 square is simply equals to P1 square plus M1 square. So if you now, put this expressions into that equation and solve for each, then you will find out a equation for this S2.
Okay.
In terms of the components.
And the other thing is that probably like you should give the physical region of S and T variables, otherwise it is not clear whether cos theta is less than bounded from -1 to 1.
Okay. Yeah. Okay. Fine. Yes. Yeah. Okay. So yeah, let me just write. Okay. So what? Okay. So this is an expansion in. So I'm in the slide of this TST expansion of the TST. So this is an expansion in the S channel. So in the S channel, the physical region is this. In the S channel, S is greater than equal to, so we are considering now, okay, let me go to the next slide. Let me just go to the next slide and. So we are from now on, we'll consider identical masses, and M is the mass. And with identical mass, I have, so S channel physical is greater than S equal to 4m square. And T physical will be determined by cos theta equal to 1 plus 2t by S minus 4m square. So cos theta is -1. That will determine T. And in the U channel, it will correspond, in the S channel only, the corresponding U value will be given by 4m square minus S minus T. So this is the S channel. So in the S channel, we are considering this. So S is greater than 4m square, because that much you need to have by the energy conservation. And T is determined by this relationship between cos theta relating T and S. And cos theta, for physical cos theta, it's 1 and minus, it's lies between 1 and -1. And U will be correspondingly determined. So this is the physical S channel configurations. So you can actually draw what they call a Mandelstam triangles. So this is like this region. This is T, this is S, this is U. So this point is S equal to 4m square. This point is T equal to 4m square. And this point is U equal to 4m square. So this upper dashed region is the S channel physical domain. This lower one is the T channel physical domain, and another is U channel physical domain. So similarly, if you go to T and U channel, the T channel, for example, T channel physical will be the T is greater than or equal to 4m square, and cos theta will be again related by virtue of cos theta you will get the S. So for example, when you are in T channel, cos theta is essentially 1 2st minus 4m square. So by that will determine the S, and the U will be determined accordingly, and all other and similarly for the U channel.
So Parthiv, while
Yeah.
drawing this diagram,
Yeah.
so it's a two-dimensional plane, right? And you are
Yes,
drawing
yes, yes.
T and U. So, like, are you keeping U constant to draw this S and T?
Yes. Yeah. Actually, yeah. This triangular structure, it actually follows. I think, yeah, right. You have to. Yeah, it's actually T and U are actually constant, really.
No, I think, sorry, I think,
So-
let me correct. I think the
Yeah,
thing
yeah.
is that to draw this figure, actually, you don't need to fix. Actually, what happens is that, like, if you are considering S channel, then S have to be greater than 4m square, and T have to be minus U minus 4m square, less than equal to, greater, less than equal to T and less than equal to 0. This in that way, so you don't have to fix the U also.
Yes.
So that's why you get the three triangle regions. Even T channel, U channel, you can just
No, so
I think
each of these sides corresponds to what? For example, the line which is drawn, this S equal to 4m square, and then goes
no,
to
S equal to 4m square, not line. This is a point, I think.
From that point, so from that point to equal to 4m square. So that line corresponds to what?
Oh. Okay. So S equal to S equal to 4m square. It's just and it's going that way, and so these are I think these are like so one line is, I think, T equal to 0, another line is U equal to 0. So
okay. I mean, yeah, I meant that. I mean, so while drawing a particular line, you are fixing some U.
Yeah. Right.
Okay.
Right. Yeah. Yes. Okay. So this is the physical region. However, the importance for studying analytics properties.
Can I ask one more question?
Yes.
So should I understand in S channel the internal particles in the S diagram goes on shell? Is that the motivation?
No. Sorry. Yeah. No. On shell. No. S channel is just okay. So that's again kinematical channel. So suppose, for example, okay, let me go to the previous slide. So okay, this is actually so in this case, what happens? You are actually right that in the S channel these particles go on shell. So if you change channels, it may happen that actually a particle-particle reaction goes to a particle-antiparticle reaction when you change the channel. So that kind of stuff happens.
In the sense, like usually if I'm doing perturbation theory, I'll draw all these three channel diagrams. But I was wondering the reason behind like calling these different channels is that I should think that when S is greater than 4m square, S channel, mediating particle can go on shell, and T channel.
No. So just don't. Like I think the main reason for this channel, naming these different channels are like is really that
what happens when S is greater than 4m square? I'm just asking that. Yeah.
What happens when
S is greater than 4m square?
S is greater than. For this reaction to happen, you have to have S is greater than 4m square because
T greater than 4m square, right? Or you
no. Here we are not taking T greater than 4m square. Presumably, if these are really non-charged scalars, it does not really matter. But suppose these were charged scalar, then it would matter the STU channel. So for non-charged scalar, you won't even make any difference. So for example, pi naught. If you're looking at pi naught scattering, STU channels, there is no difference. You will not find any difference apart from some variable change.
So if I am in the shaded region, the reaction will happen. That's the statement.
Yes. Yeah.
And what's the difference between reaction happening in any of these three shaded regions? Wait.
No. These okay. So ideally, so you know the usual kinematics, right? Because there are four momenta entering into this whole kinematics business. There is like 2 incoming momenta and 2 outgoing momenta. It depends on that. So if you think that which out of these 4 particles, which 2 you are actually sending and which two particles are incoming and which 2 particles are outgoing. So that decides that which channels you are looking at. It's really that which 2 particles you are taking colliding.
I see. So it hasn't got anything to do with what in what channel the mediating particle can go on solo.
No. Yeah. So see, all this
because in the expansion you wrote all the, like say all the poles will appear in S. So I thought only the mediating particles in the S diagram can go on.
Yes, this is the S pole something. So let me just give you one one simple just writing. So let me go to a new slide. So suppose you are considering this A plus B going to C plus D is one channel, but you could have also taken A plus C going to B plus D. That will constitute another channel, because now you are clubbing together A and AC and B. AC is one and then BD is another. On the other hand, you could have also taken so that there are many channels, of course, but then these are related by one another symmetry and so on and so forth. So ideally, I'm taking uncharged scalars, so it's like everything is nothing really happens. But if you take the charged scalars, if this is the S channel, your T channel would be this one, where C is the antiparticle of C and C bar is the antiparticle of C bar and D bar is the antiparticle of.
Understood. You're labeling channels by what you're sending in and what is coming out.
Yeah. What actual reactions?
But I'm still asking, if I have the first reaction, A plus B goes to C plus D, why should I express it as in the partial amplitude? Why should I express it as if all the apparent poles are in this in the S variable?
No. That is why. So it is in the S channel. S is your. S is your kinematic energy. So let's just say that S is the energy plane.
That I understand.
So S is the energy that you are going to vary. So S is just the given the name of this. For this reaction, S is just the energy, and in the energy variable you are going to understand this reaction. So obviously we will be looking for whatever the analytic structures and so on and so forth. It will be we'll look for the analytic structure of every variable, but yeah, in this channel we will just do it.
That makes sense. Thank you.
Okay, so right. Okay, so what we have obtained is this partial wave expansion, and so next we would like to understand. But this is we're just saying that some physical region and T is very restrictive in the sense. But we would like to understand now the analytic properties. Analytic properties of the TST, as a function of two complex variables S and T. So now I'm promoting both of the complex variables, S and T, two complex. So we are essentially a problem on C2. So we will be essentially doing a problem on C2. However, even that is the highest level of the problem. But even before that, even before going into that, why S and two variables? Because ideally there are like three variables ST and U, but they are constrained by one linear relationship. First, what we will do is actually a single variable dispersion relationship. Okay, so I'm going to the next slide. So what I will do is that was the single variable dispersion relationship. Now all of these things have been actually, some of the for example for pion-pion scattering, pi-naught scattering in all the channels, this dispersion relationship has been proved. But not all reactions, not all particle reactions, dispersion relationship has been proved. So I will briefly just discuss that, under what condition this can be proved and so on and so forth. But the essential starting point for proving these, the starting point for proving this kind of analytic properties have been historically the framework of axiomatic quantum field theory. So at that time, what does it really mean by axiomatic quantum field theory? What really went into these derivations? One was, of course, Lorentz invariance. Another was, of course, asymptotic completeness of the states, that means the in state and out state. Next, of course, we have this, what is the physical mass spectrum? Then, of course, causality. That means local commutator of space-like separated operators vanish. And finally, the tempered distribution nature of field operators. However, this last point is not really. I mean, later it was realized that these properties, these analytic properties, can also be proved or investigated without actually using this tempered distribution property. So, just to clarify on physical terms, what this tempered distribution nature results in. So, just to mention that.
Can you explain each of these terms?
Yes.
What really means, leaving the Lorentz invariance?
Yeah. So, Lorentz invariance is the usual term. Asymptotic completeness is that it is the assumption that your in state, so the space of the in states and the out states, so the in Fock space and out Fock space are complete, in the sense that you can use the kind of resolution of identity I wrote yesterday. Physical mass spectrum is that in all of these works, it has been assumed that there is a mass gap. Causality is basically it's simply that the space-like, there is no correlation between space-like events. So the space-like field operators, their commutator should vanish. And finally, this tempered distribution I'm telling, I mean, I'm not going to this mathematical thing. What it really tells the tempered distribution nature is that, what it ultimately boils down to is that scattering amplitude is polynomially bounded. So,
yeah, I had a question.
Yeah,
I think it's on the next slide or something.
Yeah.
Yeah, so
it's
just
next slide.
Yeah, just a fourth point, whatever this causality thing you explained. So this I understood in terms of correlation function when time and space variables are there. But in S-matrix, since you already gone to momentum space, how really you make sense of causality in terms of S-matrix?
Yes. Actually, all in all these proofs. Sorry, I forgot. The actual tool was the LSZ reduction formula. So in LSZ reduction formula, you relate this, S-matrix elements with the field correlation functions via this Fourier transform kind of thing. So it is through that the causality enters into this whole game.
Parthiv, we have some questions.
Yeah.
One from
Yes.
Olgo. That's in the chat. He's saying, is there any way one can guess that T should be analytic function in C2 without going to the particle feature or Lagrangian?
Yes. Okay. Yeah, that's actually that is what we want to reach, and that is what we want to really reach. And even I must say that even though we are considering here axiomatic, I am telling you field theory, at least for this. But in this, nowhere in these derivations, no Lagrangian or no Lagrangian property were actually assumed. only simple these kind of field properties were assumed. And the analyticity of T is where we are actually heading towards. So that is where we want to come today.
And
on city.
Devanshu has raised his hand.
Yeah, hi.
Yeah.
My question is, so actually you have already discussed this. If you can go back a couple of slides where you wrote down a formula for cos theta when you were discussing scattering.
Okay. So it's slide number 17.
Yes.
Yeah.
Yes. So it's sort of again to coming back to that same. Sorry, the next slide where you talk about identical particles. You have written maybe. Yeah. So my issue is, so yeah, you did point out that cos theta will be physically bounded. Although my question is, suppose I have some sort of machine and I'm fine tuning my S. S is gradually going towards 4m square. So T must go towards 0. But there must be a sort of rate of comparison in order to ensure that cos theta is strictly greater than -1 and less than 1.
Yeah.
My question is, so is there some assumption about the ratio S by T in this formula when you are doing this?
Yeah. Okay. You are actually right, and I think this is a this is a serious problem that what you really say, that as S goes to 4m square, and then this cos theta in fact can be kind of just T goes to 0. It can be. I think there is an well, I'm not very sure. I mean, I'm not very sure. I mean, I've not seen any the kind of ratios thing you are talking about, but I would say the way one approaches this is going to 4m square limit is, this is somewhat special. I mean, people take in this limit in an indirect way. I mean, for actual calculation.
I see. Another question I had is, so you introduced this. Can you go to the next slide? The last term I did not understand. Next to this.
Okay, this one. So is it where I just wrote the
last point? Temper distribution nature of field of
yes.
Can you again explain that? Thanks.
Oh yes, okay. So I wanted to so just let me just give a little bit of mathematical definition of what temper distribution means. Then let me just then I will just I wanted to avoid that, but anyway. So distribution is simply, so what is a distribution? Distribution is basically, distributions are dual vectors of function. I mean, function in the sense that suppose you have a space, you have a function space, let's say H is your some function space, and take this to be some kind of Hilbert space. So Hilbert space means, okay, so let's take it a one function over R. So Fx, where x is R, and Hilbert space means if x has finite L2 norm with respect to usual Borel measure. I mean, that means, what it really means that Fx, because it's anyway real valued, so F is R going to R squared dx, this is infinity. So let's just say that this is the some kind of, this is the H space that we are talking about. Now, let's phi be a functional, a linear functional from H to R. So we also consider that H is over the ground field is also R. So phi is a linear functional from H to R. That means phi takes as an argument F, an element of H, and it gives us R. And then phi is called, that is what is called a distribution. So distribution is basically a dual space of a function space. Now, for tempered distribution, we consider a very special kind of space to start with. A very special kind of space, and that is, so go to the next slide. So that is what called a Schwartz space. Schwartz space is basically a space of, this is a space of sufficiently well-behaved function. What does it really mean? That suppose I consider S from some function f going to R to R, but if we also consider that f is C infinity, that means f is smooth, that means all order derivatives of f with respect to R, with respect to X or R exists. And if we further assume that f goes to 0 at towards the infinity, so as x goes to infinity, f goes to 0 sufficiently fast. Sufficiently fast means that not only f but also f prime, f double prime, all orders of 0, they goes to 0 as x goes to infinity sufficiently fast. That means they goes always 0 for some faster than some inverse powers of x. Then these functions, such functions, there's a norm is defined for such functions. I'm not going to that, but such functions are really called Schwartz functions. And the space of these functions, if you give this function as a with respect to that norm, that norm, if you give that kind the usual topology, then that space becomes a Schwartz space. Now, if you consider the dual space of the Schwartz space, so we denote this by, in this case, R. So this is my Schwartz space. Then the dual of the Schwartz space, so this is often denoted by, this is the space of what they call tempered distributions. What it really means, what it actually means is this, that, okay, done. Fine, so that fixed us for us the definition of Schwartz space, and we are talking about the dual space of that Schwartz space, and this is the space of the tempered distribution. So that, okay, I'm going to the next slide. If
so one quick question. The Schwartz space is still a function of this ST Mandelstam variables, right? It is taking the Mandelstam variable to some real.
Yeah, I mean, in the physical respect, we would like to take such a function. I mean, for our case, we would like to see the Schwartz space will be a function of those Mandelstam variables, right?
Right. And this dual space, so this is dualizing to what?
Okay, it's a dual with respect to this usual vector space sense. So what is a dual of a vector space? So dual of a vector space is, suppose you have a vector space V, then okay, let me just write down.
Are you in the next slide?
Yeah, next slide, yeah.
Okay.
Dual vector space. So suppose I have a vector space V on some ground field, let's say R for the time being, can be taken any other F as well. Then what is a linear functional? So suppose a linear functional on V is defined as a map from V to this R, such that if P, then V belongs to R. But you can also endow by the so this since V is a linear structure, you can also consider a linear structure on the set of L. So this can be also given linear structure with respect to R. Then this also results in another vector space, which is called the dual vector space. So it is in this sense we are calling V bar to be dual of V. So basically, in the linear algebra language, the dual vector space here is just the space of linear functionals on a vector space. So this is my dual vector space. So just now what I told is, for example, my vector space right now is a Schwarz space, or it is also called the space of test functions, and the the dual space of that Schwarz space is the space of tempered distributions. Yeah.
Could you also... Shubham had a question. Okay.
Oh, sorry. Then go on.
Yeah.
Shubham,
so like, can you just provide an example of what you just said here?
Okay.
Like, in the sense, the Schwarz function and like because Schwarz functions in terms of Mandelstam invariants and like just some small example.
Okay. I can give you a good example of Schwarz. Okay, a good example of Schwarz function will be of this form. So let's say with respect to Mandelstam variable, I don't know. I mean, you have to just construct such a function. But a good example of such a Schwarz function will be e to the power minus x square. So e to the power minus x square will be a good example of Schwarz function, because if you see, this is a function. So let me just go to another slide.
Parthiv?
Yeah.
Yeah, sorry to interrupt, but I feel that this mathematical detour is going a bit sort of off topic. So I think these questions are valid, and I definitely don't want to discourage them, but I think Slack is probably a better channel to discuss this.
Yes. Yeah, fine. Okay.
Can I just ask one question and then end this?
Right. Okay.
Could you throw some physical motivation why we were happy with the test functions vanishing only up to second order derivatives?
No, it's okay. It's not second order. Okay, I mean, it goes on, like it's all order.
So it should vanish up to all orders.
Yeah. It's all order. So I've just written up to second order. It's all order. Yeah. Okay. Yeah, I can actually discuss this. Mathematical. Yeah, it's true. It's taking too much time. Fine. Okay. So let me just. Just mention the consequence of the tempered distribution, tempered distribution. What actually follows from that. So I've gone to the new slide. Okay. So like slide number 24. So the consequence, the physical consequence is that this is a polynomial boundedness. It's a polynomial boundedness. So this polynomial boundedness is this. So we will be considering this. So this is a polynomial boundedness we are considering an S channel. So fixed T. Fixed T is like fixed real T. There is no question of like physical or something like that, because anyway we are just going to take fixed real T. Then limit is going to infinity. This should be bounded by a polynomial where n is n is some non-negative number. So this is what actually follows quite straightforwardly. So this thing is actually inbuilt in this actually follows from this tempered distribution problem. So it is this one which essentially follows from this. And this is very crucial for writing any kind of dispersion relationship. Why I'm telling you that, yeah.
Parthiv, I have a question, like
Yes.
this fixed T is T in the physical region or for any real value of T?
No. It's actually okay. I think it's any real T kind of. So it's
and the n can depend on the U, because also you don't have fixed U, or I think U is like in terms of S.
Well, no, because I have fixed T. So essentially, n can depend on T. So that is the usual Regge boundedness people talk about. You talk about when they talk about this Regge, then n becomes that kind of T. But the point is that here, at least in this format, n is just an integer, and we will see what does it really mean.
Okay, thank you.
Yeah. Okay, so we can. So exploiting this, one can write down a dispersion relationship. So where I was there, so just go back to this. So what is a dispersion relationship? Okay. Before dispersion relationship, we also need some more. So just edit this slide here. So before going to dispersion relationship, we also need some information about the analytic structure of the TST. So I've gone to the new slide. Okay, next slide, 25 slide. So in complex S channel. So we will focus on complex S channel because this is the dispersion relationship that we are going to talk about, is called fixed T dispersion relationship. However, here T is negative. So it's actually physical T. So there we assume the kind of structure we will have. We are considering identical mass, again, remember. So of course there is a threshold. So this is threshold at 4m square, S equal to 4m square. So threshold is a branch point. So okay, there are multiple thresholds. So one threshold is at 4m square. The next threshold is at actually 9m square. The next threshold is at 16m square, and so on and so forth. And we have to define a cut plane in order to define the function, the TST, single valued in a single valued fashion. Now one can consider various kinds of, for each thing one can consider all kind of complicated cuts. So one can consider a cut like this. But because all these, whatever way you choose the cut, ultimately in the cut plane your TST is a single value. But since 4m square, 9m square, 16m square, all of them are actually lying on the same, real axis, it is most convenient to take the cut, instead of taking them all this kind of haphazardous way. It's best to take the cut from 4m square and going into infinity along the real line. So this is the S channel threshold cut.
Sorry, having one cut is very different from having many cuts.
No. It's actually, so for example, it's like 4m square, from 4m square there's a cut, from 9m square there'll be another cut, 16m square. All these cuts you are taking just along the along this axis from 4m square to infinity. This will only lead to, if you properly want to think, this will only lead to a manifold, a complicated Riemann sheet structure, nothing else.
I mean, I'm slightly confused if there's some choice or like.
No. There's so see, whatever the point is that whatever complicated way you can take the cuts, but even when we do complex integral, we always choose some kind of cut which is convenient to us, which is convenient, which will actually makes us to do some practical calculation conveniently, right? Because there are for every choice of cut you have for every choice of cut you have a choice of single valued definition of the function. So it really does not matter, whatever, but it is also important that in what choice you are being able to do some practical calculation, because we will soon write an expression where we will need this practicality is also keep in mind.
Okay, let me just say one sentence and then like I'll stop this question. But like if I just joined, I'm assuming all the branch points are of same order and so on. So then like if I just joined just adjacent branch points, like adjacent integral square squares, then I would have got a different branching, way different Riemann surface with like so many branch cuts, like but finite length. And then I would have thought all the analytic properties, like how the monotony is, how the windings and all will come out, will be very different from having one single cut. So I'm just wondering if there's a choice in that sense. Or?
Well, no, not really. Okay. Yeah, well, see, the point is that what we are, okay, to be clear. So the point is that we have a physical, so we have a physical scattering amplitude, which we actually measure in an experiment, let's say LHC or something. And we have a complex valued function TST of the variables S and T. So the point is that what we are trying to understand, the property of this TST along with the and also we will need some way to relate this TST with the physical scattering. I mean, of course, physically you are going to measure a scattering at, let's say, S more than S is greater than or equal to 4m square something. But then, of course, how we are going to make sense. So, for example, suppose you want to measure the scattering at S very much greater than 16m square. The point is that how are you going to whatever you have measured, how are you going to make that connection with the TST that we have obtained, with the TST, with the mathematical function you have at your hand. It is in this definition of the mathematical function and the connection with the physics, that the physical whatever we have gotten out of experiments, that we are making these choices. Does it make any sense?
Maybe I have to think about it, but like at least in the calendar,
I think
calendar representation, I thought the branch cut is really one cut from 4m square, not separate cuts which have been drawn together. But that's not what you're saying.
Yeah. Actually, see, we really do not talk about the calendar representation here, but yes, of course, calendar representation, from there we take the, from there people take the inspiration and put this cut structure as an assumption, really. So there is no way to prove, for example, even in the most general framework of axiomatic framework kind of that this kind of, but it takes the inspiration from those perturbative structures, something like that, and then it starts with the assumption of that. So all of this is going into as an assumption of this structure.
Okay, thank you.
Okay. So this is, but there will be also for fixed T, for fixed negativity, there will be also an U channel cut. There will be also an
Parthiv?
Yeah.
Anish has a question.
Yes.
He's asking, why did we impose the tempered distribution condition on TST?
Tempered distribution is actually
what is the physical reason?
I do not know, but I think tempered distribution is really, and it was one of the axioms with the Whitman. And I would say, in my understanding, what Whitman wanted to have a well-behaved, I think his motivation came from the fact that, physical states should somehow be suppressed at the infinities. I think that is the physical motivation with which he may have defined that. I do not know the exact details.
I guess you're just scattering test particles, which are wave packets, like lumps of particles. Then you can have your test functions to be localized. And you can make precise how localized they are.
I think that is,
then you need to work only field distributions which work well those test functions.
Because anyway, mathematically, it was realized that these operators, field operators or whatever you are talking about, these are operator valued distributions, because even in the state you are getting these Dirac delta functions, which are really distributions, and also Dirac delta function is a very, I think also the mathematical way about talking about Dirac delta kind of distributions is actually tempered distributions, because as you see, Dirac delta distribution really dies away very fast. It just dies away fast. So I think that's from that also. But I think, physically I would say that it's almost like the Hilbert norm goes to vanishes at it, something like that.
Okay, thanks.
Okay, so there is a S channel cut, but there's also a U channel cut, because here T is because you have S plus T plus U equals to 4m square. and u equal to 4m square is also a threshold. See, there may be a confusing point that what we are doing, we have so many, but the point is that even if whatever reaction we are looking at, ultimately we are trying to understand the analytic property of TST as a function of S and T. But since there are 3 Mandelstam variables but which are related by 4m square, so there's a u contribution will also come there. The question, of course, is that in an experiment, what channel you are actually accessing depends on what particles you are actually colliding or something like that. But when you're talking about the mathematical function, you will be working with this. Okay, so these are related to the threshold. Threshold is basically threshold has another interpretation that that we will see when we will study the unitarity. But really, threshold appears because whenever there is there's a possibility of going an on-shell intermediate states to be on-shell. Those are the points where things can be threshold in the more traditional field theory language. But there can also be bound states.
Can I ask a question, Parthiv? I think for the U channel scattering, you should have like you told just there will be some threshold starting from u equal to 4m square. So that probably here tells that S equal to minus T.
Yes.
So now you see that if you allow that T to be like less than minus 4m square kind of thing, then the 2 branch points from the 2 sides can collide. So it's not that for all real T you can do this thing. Probably you have to fix some value of T runs from minus 4m square to 4m square, and in that region, if you fix only, probably you can this branch are completely different. They are not colliding to each other.
Yes. I would say I mean I think that is that is the case actually. Right.
Yeah.
Yes.
Otherwise, that's the comment.
Right. Okay. And another point is, of course, that apart from this threshold, there can be poles. I mean, poles will correspond to bound states. So these are bound states. Now, bound states are actually stable particle states. I mean, they are stable particle states. So
one quick question: why cannot the bound states have like branch cut singularities? Meaning, why should they be discrete poles?
Oh, okay. I think I mean, again, what I'm telling you is this: that this is obtained. I think this is seen in the perturbation theory or something. That perturbation theory they come as poles, and what these guys took that they take Q from there and then see that these are bound states are poles. But there is a purely S-matrix argument. But I guess overall these are taken as an assumption that the bound states will appear as poles. Right. But I also I think in the propagator, when we write down a propagator, in the propagator, like for example, what is the propagator? Like propagator is like p square minus m square. So for a particle and for a stable particle, I will always have a pole. I think so. This is also the same thing for the bound state. So it's like there's a stable bound state, there's always a pole. Okay, so there can be also bound states and thresholds. But I mean, it will. Now here you can actually. But there is yet another question left, and that question is this: that how the physical scattering amplitude is related to the mathematical function TST. So this is something that's called. This is by saying that the physical scattering amplitude is a boundary value of the TST, because physical scattering amplitude is a boundary value of the mathematical function TST, which is analytic everywhere in the cut plane except possibly at the poles. So that means the mathematical definition is this. It's just what does it really mean? That suppose you are looking at a scattering amplitude, actual experimental scattering amplitude for S greater than 4m square something. But since S equal to 4m square is a threshold, and there is a branch point setting, there is a branch cut. So you have to be very careful about how you are going to approach that branch cut to get that value. How are you going to approach that branch cut from which direction? So again, this criteria or this criteria is really really inspired by the Feynman I epsilon prescription that is usually done in the field in perturbative calculation. That first what you really do when you add this I epsilon, you first give a dent to this branch point into the lower half plane. So you push the for example 4m square into the lower half plane by incorporating an I epsilon. Sorry, so it's a minus. So first you do is that you put a minus I epsilon and then you push this branch point in the lower half plane. Then you can approach because now it's a 4m square plus 4m square minus I epsilon. It is dented into the lower half plane. Then you can now approach the TS. Now you can safely take the TST from TST in for S really greater than 4m square. But then you would really like to go back to the original threshold that is in the 4m square. So you would really like to take the epsilon back to 0, which is, so taking this 4m square minus epsilon and epsilon goes to 0 is equivalent to starting with an TST, but not hampering the position of the 4m square, but starting with T slightly above in the upper half plane and forcing the TST itself towards the branch point or towards the branch cut structure. So this is what they call. So this is what is basically the boundary condition by which the physical scattering amplitude is related to this mathematical function of TST. Okay, is there a question?
Yeah.
Yeah.
So I mean, usually you want to push the poles away from the real axis because you're integrating over the real line. Here, there is no. I mean, why do you want to do that?
So okay, so once again, let me tell. So for example, suppose physically I can measure the physical scattering amplitude. I can measure the 4m square greater than 4m square any energy. But the problem is that suppose I have this function TST. So TST 4m. So suppose let's say I have a 5m squares. I'm looking at this function as a 5m square, but 5m square is greater than 4m square. So it's basically which phase I'm going to choose. So if I go from the above, I'm going to pick up one phase, but if I'm going to go from the below, I'm going to pick up another phase. So it is to fix up that which phase corresponds to the physical scattering amplitude.
I see. Okay.
Yeah. Okay. So,
sorry, Orko, do you have a question? In the chat.
Yeah, I thought that probably I missed it. So, Parthiv, what is the order of these branch cuts?
Okay. So there is this thing. I think for event dimensional field theory. So, for example, for 4-dimensional field theories, or this branch point is actually a square root kind of branch point, and for odd dimensional field theory, it comes out to be a logarithmic kind of branch point.
For logarithmic for what?
So for odd dimensional field theories. So suppose let's say three-dimensional system.
Okay. But for event dimensional, it's just square root.
It's a square root kind of.
Okay. Thank you.
Okay. So So this explains the one. Now there is yeah.
Please go ahead.
Hi. So did you explain why is it plus epsilon or no? Why not minus epsilon?
I just showed that it's actually inspired by the usual that Feynman prescription. That in the Feynman prescription, what you do, you basically push this 4m square or something like that towards down a little bit in the lower half plane, and then whatever you do stuff, and then you let this 4m square to again seep back. So what that is equivalent to actually with this, starting the TS to be from an upper half plane, and then you let the TS to so this is how it's defined. So the T physical will be defined by this prescription.
Okay.
Okay, so there is another thing, and this is important, is this that suppose I want to analytic. Okay, I'm going to go to another slide. So I have a branch point, of course, from here, and let's say a MB is a pole position, and let's say this is for M square. So I have the TST sitting in this where, but now I can analytically continue from from 4m square. So see, 4m square, the TST, the physical TST is obviously the 4m for s greater than 4m square. But now I'm going to analytically continue it to the region between MB square and 4m square, and we are assuming that MB square is the closest. I mean, in a sense, it's the farthest bound state. That means there is nothing in between MB square and 4m square. So between MB square and 4m square, it's actually analytic. The TST is perfectly analytic. So not only it's analytic, but also here TST is real. This is also important to understand. To take that this is here it is real. So it is analytic and real. Then there's a principle in single variable quantum mechanics. By the way, now you realize that T is real, so we are just doing single variable complex analysis. S is just complex. So there's theorem, Schwarz reflection principle, by which you can analytically continue also in the lower half plane. So suppose you start from some point, let's say it's some S0 where S0 is greater than 4m square, and you analytically continue to this real segment between MB and 4m square. But you have also assumed that this TST, I mean, forget about T, TS as a function of S is analytic in the upper half plane. Then analytic in the upper half plane, as well as it is real in this real domain between MB and 4m square. Then by Schwarz reflection principle, it tells that you can analytically continue into the lower half plane. And if when you analytically continue into the lower half plane and you reach the same S0 by doing this analytic continuation from lower, what you will reach is S I naught minus I epsilon equal to T, but this will be equal to T star S plus I epsilon T. See, the important point is to relate this complex conjugate of T in the upper half plane to the analytically continued part of the scattering amplitude in the lower half plane. So this follows from Schwarz reflection principle, and it was absolutely crucial. This is, you have to understand that it is absolutely crucial to have this real domain between MB and 4m square. If we had not, I mean, if we have to have such a region where it is it's absolutely analytic and real. That means there is no branch point, there is no poles and whatever so forth. It is through that portion we will actually, for example, we have been able to do this analytic continuation. To contrast this situation, let me just mention one thing, that suppose for massless case, in the massless case, the entire real axis will be actually branch cut, because now your 4m square is m equal to 0. And then we do not know how to run this kind of argument, because really your entire this thing is now running as the branch cut. So is this thing clear? Question, if any.
I think
any question?
I was just asking that this T equal to T star, what you have said. I mean, you can just think about it as some e to the power I theta, you're just rotating it by 2 pi. That would also make sense. So is it also true for this branch cut if that is logarithmic branch cut? This T
yes. So it's basically, I mean, as it just depends on that, you know. The only problem was that we are not being able to go. We are not being able to go into that because at the outset, this is the most general function. We do not know what went into that. I mean, the information that it's a logarithmic branch cut only comes through a partial wave coefficient. There you actually realize. But whatever it is, the branch point structure is there. This is always true.
I mean, like, yeah, one can see it like it's just a rotation kind of thing, right?
No, it's not just a rotation. It's not a straightforward rotation, because the problem is that in the most general case, okay, maybe I was wrong to say that the T, it's so what I said, that the square root branch cut structure or the logarithm branch cut structure, they actually are of the partial wave coefficient that I wrote before, like ALS something. So okay. For TST as a whole, but yeah, you may think that okay, because these are ALS, but this is not a priori clear that this is not a priori given that why this should be equal to this. So if I'm just given the in the so okay. This is because this is requiring something like that. So what this is writing in simple terms is if f star z equal to f z star. Now you may not be able to do it for any, I mean, all kind of arbitrary functions. So that is why the importance of the Schwarz reflection principle is that you are, you will not be able to do. I think this kind of argument come much before, for actual exploration of this kind of the later.
Only true for epsilon small, right?
Yeah.
This is only the thing that you wrote. It's minus I epsilon and equal to T star. This is only for epsilon small epsilon, right? This is not for generic epsilon.
Yeah. It's actually epsilon small. Yeah, right. Very It's like epsilon goes to 0 plus.
So it's not actually similar to f star z equal to f of z star.
Yeah, I mean, you can think of. I mean, of course, in this small domain. I mean, this is a very. Of course, the whole point of doing that was interesting was that to relate this upper half plane and lower half plane to this thing. But the reflection principle tells you that you can do this analytic confirmation in this fashion, this kind of fashion. Okay. So I can actually discuss this more later, perhaps.
Yeah. This statement is true only for real T.
Yes, because see the point is that it's real T. It's we have made this statement. And this theorem, this Schwarz reflection principle, it is only a theorem for
Parthiv, I think your voice is breaking.
Complex analysis. So it's just so that's why we are in complex. Oh, is it? Am I not audible clearly?
You are audible now, but can you just repeat?
Okay. So yes. So does this Schwarz reflection principle is really this is a theorem for a single complex variable. So for multiple so when you want to fully elevate to two complex variable in order to suppose you wanted to understand to its full extent, then you will need more sophisticated argument kind of stuff. This kind of this argument will not really work there. So when you
Parthiv, you mentioned something about this massless particles, right? And that
yes,
branch cut will extend all the way. So what is the remedy?
Yeah.
I mean, you can have external.
Yes, but yes, of course, and that is the problem, that I don't think there's no satisfactory study of these kind of stuffs for massless S-matrix. I mean, there are some work by Steve Giddings and Porto, but I think it's still not clear how to do this. And this is a real challenge, and this is actually the problem, that you have to do it. Not just massive particle won't do this. This kind of stuff should be done for massless particle.
Okay.
Yeah. Okay. So okay. So this is the structure. So this was for T and in the complex explained. And also remember. So let me just similar things are happening in this plane, and there's this, of course, U channel bounds are also sitting on. Okay, so now with this information, that means it will have TST is holomorphic, so TST is analytic. If we assume, so what are the three things that went, that there is a bound state. From now on, we will ignore the bound state. Oh, another thing that I will forget to say. So that is, so because it has a branch point structure. It has a branch point, and you have there's a cut and so on and so forth. And in cut plane, is to make it single valued, and choose this cut plane. There's another way of course describing this multiple valued function is this through this sheeted Riemann surface structure. So let me just
Parthiv, just
yeah.
Still, since you are here, so this branch cuts in the positive axis and branch cut in the negative axis, they are in two different complex planes, right? One is for S and one is for T.
No,
right?
no. So no. This is so this is, so for example, if I fix the T, so T is fixed in that. So suppose T is fixed. So there is a S channel, and then so in the S channel there will be a threshold, let's say at S equal to 4m square. Okay. But for fixed T, there will be also a threshold for U greater than m square. In the U channel, for U channel there will be also a threshold. Now, because S plus T plus E equal to 4m square.
Okay. So this is in the S complex plane itself.
Yes.
Okay.
Yes.
Okay.
So you can express the U channel also in terms of the S channel.
Okay.
Yeah. Okay. So yeah. So what was I telling? That of course, there's a cut plane, and you can think of this function as is analytic in the cut plane, and it is analytic in the cut plane. But there's another way of seeing this whole thing, is that you go to the sheeted Riemann surface structure, and if you do that, clearly you have one sheet of Riemann surface, which is when you have not taken a round around 4m square. But if you are crossing, if you cross this branch cut, then you will land up on another sheet of the Riemann surface. So if I just look at from the 4m square, so there are essentially at least there are two. There are two Riemann sheets, and the relation. So there are two Riemann sheets, and one of them is called physical sheet, and this physical sheet is the sheet on which this on whose so physical sheet is the one from where you are going to approach the physical scattering amplitude as a boundary. So if you are on a physical sheet, so this relationship, when we just go back to the previous slide, so it is this relationship when I'm saying that Ts plus I epsilon T and limit epsilon goes to 0, this is equal to T physical St. What it really tells you is that you need to, in order the T physical St, you need to approach the boundary in the physical sheet. That means you are not crossing the branch cut, and you are being in the physical sheet, and from that physical sheet only, by being within the physical sheet, you are approaching the boundary of that physical sheet. Then you will reach the physical scattering amplitude. There is another sheet, and this is, and all this I'm telling you. For example, these bound state poles, and this is very important to understand. These bound state poles are really on physical sheets. But there can be also poles. There can be also poles on the second sheet, and these are actually these poles are on physical sheet. Let me just write it down. So on poles on physical sheet. So if you go to the next slide. So bound states are poles on the physical sheet. They are physically bound states, but poles on second sheet are resonances. So resonances, recall, resonances are unstable particles. Resonances are unstable particles. So they have a lifetime, really. Now, while the one crucial question is that why unstable particles are actually, why resonances are also considered to be poles. There are two arguments. One argument is really that there should there should not be any difference between a stable bound state particle and an unstable particle with long life. So that should not it's physically a reasonable thing to consider is that there should not be any mathematical nature should not change between a bound state and a resonance. And also it's for example in the quantum mechanical case, in the quantum mechanical scenario, when you see this in the quantum mechanical scattering, we have seen these resonances coming in these Breit-Wigner formulas. We have seen these resonances come as poles, only poles with a negative imaginary part. So that is what has led to this structure that resonances are actually poles on the second sheet of the TST function. So yeah, does this make clear? Have any question?
Okay, go on. So I had a question. Sorry.
Yeah.
Someone else asking something. Yeah. So I thought usually if you have a function with cuts and poles, all the poles will be identical in all sheets, and only the isn't that true?
No. What? Pardon. Once again, can you please tell me?
I thought if you have a function which has a branch cut and various poles, I thought all sheets will be identical. Isn't that right?
No.
With respect to the poles, if I look for the poles, there will be a representative of the pole on each.
So for example, the important point is that the branch cut will have, of course, the branch cut will have branch cut will introduce a sheet structure, but then on different sheets there can be there can be poles. So those poles are actually different because they are on the different sheets, and because they are different sheets, you are not going to in order to reach from one pole to another pole, you have to kind of burrow through the cut the cut junction through which these two sheets are joined to each other. So it's so it's almost like this. So suppose you have a
Sorry.
Yeah, ask us.
Yeah, so I was trying to understand what you were describing. So first we were enhancing the domain of analyticity, right? And in that way, I mean, is it same as going from one sheet to the other?
No, we have not really enhanced the domain of analyticity. We have, well, the way I am actually really describing is really, it's because I'm not told you the intermediate state, but yes, the way I'm describing is that, of course, the point is that when I told you is that it is in the, for example, when I'm telling you is this in the cut plane. So in the cut plane, you have this absolute analyticity kind of stuff. But then the thing is that suppose I have a z to the power half. So suppose I have a function fz equals z to the power half. I can think of that as I can define that to be a single valued in the cut plane, but I can also describe that as a function of one variable, and I can actually embed that in C2. And that is what ultimately gives rise to this idea of Riemann sheets. So now I'm just telling that, think it in terms of the Riemann sheet, so that really your branch cut has, so whatever I've been talking about this cut plane, that has been, that information has been translated into this sheeted structure. And all these poles and whatever these poles and that you are talking about this, whether there is any pole on those sheeted structure or something like that. So poles will be really a dent on those surfaces if you can embed that into MC2 kind of stuff. Is it clear?
Yeah, okay, I see. But then why are you calling the other sheets, the singularities on the other sheets as resonances? Meaning,
okay.
I understand. For example, you will have this spiraling, say going from one sheet to the other, and then probably they will differ by some integer numbers and so on. So in that way, like there will be some additional singularities, and those you are calling them as resonances. Is that correct?
So actually, when you go to that, when you really go to that side, it really will pick up an it will really pick up a negative imaginary part. And that way, so for example, there will be so resonance has this, so what we have is so we will often have this IET form, but when that pick up a negative resonance stuff, so suppose the I E prime t, that leads to an e to the power minus e prime t. So that is actually an unstable, a decaying state. So by resonance, what I mean is basically a decaying state. And when it goes to a second sheet, it will pick up a negative imaginary part. That's what I mean. Is it clear?
Yeah, okay, thanks.
Yeah, Parthiv, I just want to point out that it's already 4 minutes past 4. And maybe try to sort of reach a suitable point within next 2-3 minutes.
Yes. Okay. Okay, fine. Okay, let me just tell you this. When you do these things, you can write a fixed T dispersion relation shape. I mean, you can write a fixed T. Of course, since there's a polynomial boundedness n, it's just write down the form for you just quickly. So the form is something like that. T S T is not T plus S minus S naught delta S T is not T S minus S naught square. So plus there's a U-channel contribution. So this is a dispersion. This is what a dispersion relationship looks like. But this is now here I should tell that it can be shown that this n can be at n can be maximum. The maximum value can be n is actually 2. So really, the polynomial boundaries is less than a square. So this can be shown. So starting from Trossard bound, it can be shown that. I mean, it has already been shown that. So this is the a fixed dispersion relationship for S, where Ts really is imaginary part of T, which is basically the discontinuity of the T across the branch cut. So let me just quickly tell you the derivation, the way you do derive. Let me just go to a previous slide, slide number 25. So what you really do is that you start with a Cauchy integral, and then you deform the contour. Now in deforming the contour, you are actually assuming that kind of analytic structure that I told you. But it is the simplest way of saying, but it's a much more complicated stuff. And when you deform the contour, you can deform the contour to be ignore the bound states for the timing, and they can be also taken care of. But it can be deformed to a cigar kind of keyhole kind of contour around the branch cuts. And when you do that across that branch cut, whatever the contour is wrapping that branch cut, it takes up the discontinuity, and finally you reach you reach this kind of dispersion relationship. So this is a fixed dispersion relationship. However, this is not, it has not been derived for all kind of reactions. For pion scatterings, it has been derived in all channels. So, and this dispersion relationship is also not valid for any T. There is always a maximum most negative most negative value of T for which this kind of dispersion relationship is valid. For example, for pion, this value is 28 times mass of pion square. And there are many other reactions for which this can be proved, but again, it cannot be proved for all. That's why dispersion relation is not the very good way of discussing this. But it is also this is definitely a very important way, part of the analytic property of the scattering amplitude. Yeah, fine.
Parthiv, I have a question. Is that this n less than equal to 2 you are telling, like, is that similar to the case that like it is bounded by the spin there, and since you are considering QFT, so up to spin?
I think if you want to, I think maybe in the QFT framework you can give that kind of a interpretation. But when these guys derived it, there was no QFT interpretation. At least they did not give any particular interpretation. Something like that.
So it's not that I think the Siraj and this group Subham, then they assume that for gravitational theory there is a square.
Okay. So one of the point is that first of all, gravitational theory is a massless theory. So I don't know. I mean, these things won't really work there. So it can be. I mean, if there's a very consistent and well-known theory of gravitational, S-matrix will be developed. Once it is developed, then one can show that whether the same this in less than 2 follows from similar kind of thing. For that, one has to really derive a Frossard bound for massless particles. But there's an expectation that Frossard bound for massless particle will be really a polynomial kind of stuff, as opposed to logarithmic nature of for the massive particles.
Yeah, I'm not sure about this n equal to 2 bounded net, but if for general n, probably you can have a finite number of subtraction and you can write down.
No, actually, when so if along with this and when you have this Frossard bound, so Frossard bound really goes like I can discuss this in later details in Slack.
Okay.
That Frossard bound really goes like, but let me just point out the key point that Frossard bound goes like S log S. Okay. So it goes like S log square S actually. So,
right. Yeah.
So S log square S. So that is for an S channel, but you can consider also U channel, a similar kind of stuff. And there also you find out a similar kind of bound. And then you apply what is known as a theorem called Fragment-Lindelof theorem. And using that Fragment-Lindelof theorem, you can actually show that it will have, I mean, this n can be at maximum, it can be 2.
Okay, thank you.
Yeah.
Okay, I think we should thank Parthiv for this wonderful lecture. Please unmute yourself and clap. So I think we can pause the recording here and people can ask questions for 5 more minutes informally. Okay, welcome back. The last lecture of today, Arpita is going to tell us about holographic complexity. So over to you, Arpita.
Thanks, Shivani. So yesterday I went through CV computation. Maybe it was too much calculation and maybe people were not being able to follow it properly. So today I will give a short recap and then I will forward with the CA conjecture. So for the holographic complexity, whatever we have till this point of time, whatever we have learned, that for eternal black hole, evolution of Einstein-Rosen bridge in the interior cannot be described by entropy because it grows with time, which is much more than the thermalization time. So for that reason, we need to propose a new quantity, which is known as holographic complexity, which describes the growth of Einstein-Rosen bridge. So this eternal black hole, which is a two-sided black hole, which you can think is a crystal extension of a ideosocial black hole, that bulk geometry is dual to the thermophile double state at the boundary. So normally this is this eternal black hole has a killing vector tau, which is a time-like killing vector, and it can evolve under HR minus HL, but under this Hamiltonian, the TFD states remain time independent. But if we consider the Hamiltonian as a combination of HR plus HL, then we can show that the TFD state gets a time dependent phase, and then we can compute the volume of Einstein-Rosen bridge using the CV conjecture. So CV conjecture was that C was proportional to volume by G into L. So L is an arbitrary length scale which dependent on the background geometry. So for that reason, that CV conjecture, whatever the definition of complexity, is not universal, because it will always depend on a length scale and on a background geometry. However, the asymptotic growth rate of DCVDT goes to a constant value which is proportional to energy. So for that reason, there was another conjecture which was complexity equal to action. So today I will talk about more complexity equal to action conjecture. So complexity in action conjecture, it equates the boundary complexity Ca with the gravitational action evaluated on a region of space-time which is known as Wheeler-DeWitt patch. So this Wheeler-DeWitt patch is the region bounded by the null surfaces anchored at the left and right times. The speciality of this patch is that this patch contains the entire family of space-like slices, is the slices of space-like at TL and TR. So then the CA will be the gravitational action on the IWDW patch, right? So if we have an eternal black hole, which is a two-sided black hole, and so there is a TL and TR. So the WDW patches draw light rays from this point, and this patch contains all slices which are space-like at TL and TR. So various features of this complexity using action conjecture and complexity using volume conjecture do not agree, such that for CV, if DCVDT grows like this and it gets to a saturation which is proportional to TS. So along this axis is DCVDT with T. But at the same time, if we consider DCA-DT, we can see that for neutral black hole, initially it is 0 till a time, then it is negative and divergent, and then it shoot up, and then it grows, it tends to the constant value. So this is energy or proportional to TS. So this difference of these bulk quantities are probably related to differences in the microscopic definition of complexity in the boundary theory, which will be which can be understood in as the choice of elementary gates, but it's still not clear to the still not clear in the literature that why this basic difference come up.
So they are both converging to the same value or different value?
Yes, asymptotically it's proportional to energy. So there is some constant, but it's proportional to energy.
So it goes beyond the CV. As CA calculation goes beyond energy and then again comes back.
Yes, then it again come back. Yes.
But can you just go back to the CV, DCV, DT?
Yeah, it's get down for it comes from the down and then it goes.
Okay.
Yeah.
I had one more question. Can you go back to the earlier slide? Can you just remind the definition of Wheeler-DeWitt? I mean, in the sense that in the left-hand side figure, shouldn't the two backward protruding light rays meet at the singularity in the wiggly lines downstairs?
Yes, yes. So there is a time which is called TC. So TC is the critical time that corresponds that this bottom vertex of Wheeler-DeWitt patch touches the past singularity. So when this diagram I have drawn from T less than TC. So when there is a T greater than TC, then the diagram will be. Then the bottom, this will be the two null boundaries will join the here. Is it fine? Devanshu?
Yes. 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 Thank you.
Yeah. So this geometry is symmetric under t goes to minus t. And but for the volume calculation, we have shown that we have only considered that t greater than 0 maximal volume slice. So for this case also, we will consider the behavior of complexity for t greater than 0. But as they are symmetric, you can get the lower part for using CB conjecture. The lower part of the interior horizon or like this region was not accessible, but using CA you can use this. You can get the result for these areas also. So now I will evaluate. I will show that how to compute this gravitational action on the WDW patch. So first I will consider T less than TC. So the Penrose diagram will be. So this is here I am introducing a cutoff near r equal to 0, which is r equal to epsilon 0, and near r equal to infinity, which will give me UV cutoff. So that is r equal to r max. So so for this Wheeler-DeWitt patch, these lines are u equal to constant line, and this v equal to constant line. Here uv are Eddington-Finkelstein coordinate, v is Eddington-Finkelstein infalling coordinate, and u is Eddington-Finkelstein outgoing coordinate. So and r star is the tortoise coordinate, which I discussed yesterday, and that is defined as so r star is regular at horizon. So now first I will describe that what is TC. So I already told that TC is the time where the bottom vertex of WDW patches touch this r equal to 0 past singularity. So in this line along this right line, u is constant. So I can, and when it is touches to the the bottom vertex touches the past singularity, I can put the u equal to v, and for that relation I get that for TC is to r infinity star minus r star 0. So this is just the derivation like this. So this at this point, what I'm saying, this vertex at this point, the v will be r star. So it is past singularity, so r equal to 0. And as according to this, and in this line u is constant, so u will be, and which is u infinity, which is tr minus r star infinity. So equating this to where tr is tr, tl is t by 2, sorry. So using this thing, we're using these relations, and we choose TR equal to TL is equal to T by 2 from the symmetric configuration. So from this we get the TC. So we will show that for when there is the time regime where T runs from 0 to TC, the action do not change and with time, and it does change for T greater than TC. So now I will write that what is the gravitational action consists of which term. So gravitational action consists of the bulk action, which is the on-shell Einstein-Hilbert action. Then it consists of the boundary actions, where these boundary actions, boundary terms come from the Gibbons-Hawking-York term for smooth time-like and space-like segments of the boundary. Then there is a joint terms, joint between space-like and time-like segments. So boundary terms will come from space-like time-like surfaces, and it also comes from null surfaces. And joint term also will come from the joint of space-like time-like slices and null and space-like slices, or null or time-like slices. So the I bulk will be.
Can I just go back and just, I don't understand, but so not don't understand. Just can you just repeat the statement that you said that up to T equal to 0 to T equal to TC, I will not change or will change?
The complexity will not change.
Okay. The complexity is your I by some pi h, right?
Yes, yes, yes.
So we are saying that T up to T equal to TC, this I will not change.
Yes, this I will not change. Yeah. Okay. I will not change. Yeah, I is time independent.
Okay.
Yeah. Yeah. So this IB will be the Einstein-Hilbert action. So I am considering D plus 1 dimension. So now this is the bulk action. Then for the boundary terms, there will be for space-like and time-like slices, there will be Gibbons-Hawkins term, where the H is the induced metric on the space-like surfaces, and K is the extrinsic curvature. So trace of the extrinsic curvature. And then the joint terms will come. So this joint term I am writing, which is due to the intersection of space-like or time-like surfaces. These are known as Hayward joints. And then for null joints, for joints coming from intersection of null boundaries, null and either one null, one space-like, or one null, one time-like. This is kappa. And then another term which is coming due to the intersection of two null boundaries.
Obviously, can you just go over it again, the whole action?
Yeah, so
Eta,
whole action.
kappa, A. No, that's only the joint part. What
Yes,
is
yes.
it, eta, kappa?
Yes, yes. So for the first term, I told you already that this term corresponds to the joints of two space-like or two time-like surfaces, or space-like or time-like surfaces. So eta is the boost angle between the corresponding normal vectors. Sigma is the induced metric on the surface, like on the joint. Okay. And then there is a this second term. Second term is that if you have one null surface and one space-like or one time-like surface, so then this kappa is defined as So as there is a null boundary is there, so k rho kappa mu is, I'm sorry, k mu is kappa k mu. So this is a equation for a null geodesic, and these k mu's are the dx mu d lambda, so tangent to the curve, and kappa is arbitrary for null geodesic. So for time-like geodesic or for space-like geodesic, you can fix this. You can normalize the right-hand side and put it +1 or -1. But for this case, is arbitrary for. And so, and here gamma was the induced metric on the null hypersurface, and lambda is the parameter on the null surface. Okay. And the last line where it is this this term is this joint term is introduced when there are two null boundaries intersect at one point. So I'll come little later to this term.
There is a question in the chat from Pratik. Pratik is asking, isn't there be a contribution from counter term?
Yes, so for the last term, you can introduce a boundary counter term, which will help you to nullify this arbitrary parameterization, which I will talk little later.
Arbitrary parameterization meaning this lambdas and all, or the kappa?
Yes, so this A can go to A plus A0 because it's not the null vectors lack a proper normalization. So for that reason, I can introduce a boundary counter term, which in terms of these A's, and which will help me to get rid of this parameter. So that boundary counter term ensures that your action is reparameterization invariant.
Okay, I think if you want, do you want to add anything, or is it fine? Okay, you should carry on, Pratik.
Sorry. So my question is not for the joint term, on the boundary term itself. This is not this counter term actually. For example, without the joint term, there should be another counter term for which carry the divergence of the bulk term, right?
Divergence of the bulk term.
Yes. For suppose for a action in ADS, there is without any joint term. So there is a Einstein-Hilbert term, and there is a Gibbon-Hooking term which takes the which is due to the we need a well-defined variational principle, and there is a counter term actually which takes to carry the divergence of the bulk term itself, not any joint term. So isn't there be another extra term for this?
I'm not sure. As far as I know, there is a boundary counter term which is introduced due to these null boundary ambiguities.
I'm confused actually. Okay, anyway.
Okay, I think Pratik, let's move it to Slack and just carry on.
Yeah. Sure.
Or if somebody want to answer, they can answer in chat or probably come back up.
Yeah, so for these joint terms, one can look into this paper 621.00207. So this paper is written by Leonard Myers, for Poisson and Sorkin. They have talked about this gravitational action with null boundary, and they have discussed these terms very explicitly. So one can go to this reference for a further check. So now this k mu's, in this geodesic equation, we will choose that k mu dx mu is a outward directed non-normal. And by choosing normalization appropriately, we can choose this kappa equal to 0, because the boundary variation of a bulk action is well defined for constant kappa. So we will, for our further calculation, we will choose kappa equal to 0. So this second line, this term will not contribute. So only we will consider the first term and the third term for the joint contributions. So now I will briefly explain that how these joint terms looks. So these will be our non-smooth boundaries. So if we have a different kind of a space-like and time-like surfaces, so if we have this kind of a surface, where this is the joint. And similarly, if we have this kind of joints, T1 and T2 is outwards normal. We can write the boost angle, which I was saying, that eta, which was involved in these Hayward joints, as T1 dot T2, where the sign of eta will be depends on So here T's are the time-like normals. So Ti will be -1. And N is the auxiliary vector, unit vector, which is in the tangent space of the appropriate boundary region, orthogonal to the joint and pointing out from the boundary region. So this N cap or N cap will be like. So here the joints are like there are, we have considered joints between two space-like surfaces. So now we can consider two time-like surfaces. So these are the space-like normals, outward normals. And here the auxiliary vector field, auxiliary vector. Similar kind of a joint will be. So for these cases where two time-like surfaces are meeting at a point, the boost angle will be given as and the sign of the eta will be determined. And then another kind of a Hayward joint is that where there is a time-like surface and space-like surfaces are intersecting. So for this case, the boost angle will be. And the epsilon is the sign of this N2 dot N1. So epsilon is. So for these joint terms, you can also look in the Hayward paper, which is. So now the next the next thing to consider is that if we have a combination of null joint and null boundaries and space-like or time-like boundaries are intersecting. So for this case, so for null case, the problem is like that there is a no proper normalization associated with the null vectors. So the normalization is the tangent to the null curve and normal to the null curve are equivalent. So we will choose the normalize or auxiliary vectors as unit vectors, but the signs will be independent of the normalization of these vectors. So if there is a null slice, this is a null boundary with an outward normal. This and similarly this kind of a curve where this look like a knot. So for this curves, this is the A which I introduced. So now I'm writing this A, which I was asking before. Where epsilon is. Another kind of a joint cell. So so for this also you can get the same A expressions. So it will just now K, that will be the dot product of K1 and N2, and epsilon we can determine in the similar way, which I'm not writing anymore, because it is same. Look alike. So here the K's are the null vectors, K caps are the null vector, that is in the tangent space of appropriate boundary regions, orthogonal to the joints and pointing outward from the boundary region. So now I will talk briefly about the ambiguities involved in these null boundary terms. So the boundary terms associated with null boundary surfaces and null joints are somewhat ambiguous, because by construction the variation of the boundary terms is well defined and cancels the corresponding total derivative term coming from the variation of the bulk action. However, when we are evaluating the gravitational action on a particular spacetime geometry like this particular WW patch, it will generally yield different numerical values depending on your choice. And we have already said that kappa, we can choose kappa to be 0, because for kappa constant is gives us a appropriate boundary variations like delta S, delta G loading. But for the null joints, this A, whichever I have this A involved in these joint terms, depend on the arbitrary normalization, because if there are two null vectors, so K1 dot K2 will be something like alpha square, where alpha is arbitrary. So this so there is an arbitrary normalization associated with this null tangent K alpha. So we can add an additional function A0 to this A, which remains fixed when the action is varied. So we can get whatever extra term I will get, that will not be time dependent or anything. So we can take some cure for these ambiguities. So one is like this ambiguity in kappa can be easily resolved by choosing the generators of the null boundary surfaces to be affinely parameterized. So we will choose that the generators of null boundary surface be affinely parameterized. Then we can take a particular choice for A0 at the null joints, which generate additivity for the gravitational action. But these choices then leaves only the freedom to rescale the affine parameter lambda along any of the null boundaries by a constant factor. This ambiguity can also be removed by imposing a normalization condition on the null normals near the asymptotic ADS boundary. So near the asymptotic ADS boundary, we will rescale our null normals by an overall constant.
Can you just remind me what was this A naught that you got from that third term? Just like going back a few slides.
Yeah, so here as there is a no fixed normalization, so these A's are the A's we can write in terms of these normals, the normals to the null boundaries and normals to the space-like boundaries or time-like surfaces. But now here the K's are not affine. K's are not K's normalization of K is not fixed. So for that reason, I can add another term to this A, which will give me the same result.
But if you choose different A0 and also, does the complexity depends on that choice or?
Yeah, the problem is like the DCDT depends on this A and A0 stuff. So,
right, that's why I'm asking.
Yes, yes. So you need to fix it. Yeah.
No, I mean, if it depends on an arbitrary choice,
yeah,
then how can you compare it with like even how for DCV when you calculate it?
Yeah, for DCVDT there
don't
was
have,
not this kind of a
right,
term, but
right.
here for this consideration of null boundaries, you are getting these extra contributions. So this A or like this ambiguity corresponding these null vectors or null boundaries, you can to compensate that you can use this boundary counter term. So you will get in your DCADT calculation there will be terms which will depend on A. But
it's probably Davies ringtone.
Yeah. Yeah, so this will depend on A, but if you when you are adding the boundary counter term, that so I told you that these two normals I can the normalization is alpha. So my result will also depend on this alpha. But
right, that's okay.
Using that boundary counter term, I can cancel out this dependence.
So finally, when you calculate the final,
finally,
the plot that you showed,
yes,
DCADT, that doesn't have any arbitrary term, is it? Is that what you are saying?
Yes, yes, that will not have any arbitrary term, but yeah,
okay.
It will be different for different theories. But for one system, like if you are considering one ADS black hole,
right.
you will get one CA result, and then your one DCADT will approach accordingly.
Ah, okay.
The late time behavior will be similar for all. Okay. Yeah, so near the ADS boundary, I will set that Ki by T is equal to plus minus alpha, where T cap is the del T. And alpha is a positive constant if you take the time flow in the boundary theory properly. If we assume T cap is a future directed on all boundaries, then the plus sign, I will choose plus sign for the future null boundary of WDW patch, and I will choose the minus sign for past null boundary of the WDW patch. Plus is for future null boundary. These signs will come for these joint terms. So for that reason I'm mentioning. So now I will explain that what is this boundary counter term. So the boundary counter term is which will help us to remove this dependence of alpha. So that is defined as so here the gamma is the induced metric on the bundle of null generators and theta is the expansion parameter. So gamma AB is the induced metric. On the null generators. And theta is the expansion parameter which is defined as or you can write it as lambda log. And this here we have introduced an L tilde. So this L tilde is an arbitrary length scale, which you can fix later depending the specific background you choose. So this counter term will make the action invariant under reparameterization of the null surface. So now I will first talk about the bulk action. So we know the action of the W2W patch, action of a W2W patch is divergent because the space-time region extends all the way to the asymptotic ADS boundary. So for that reason, we will regulate this action introducing a cutoff surface at R equal to R max. If you want to study the divergences, you will take R max to the zero limit and you will see the divergences. So for CA, like for if you are calculating CA, you will sometimes get divergent contributions. But DCA DT, for DCA DT, you can see that these divergences cancel out among themselves when you calculate the time derivatives. And for the at the past singularity and the future singularity also, we'll introduce another cutoff surface, which is at R equal to epsilon 0. So the bulk action will be the S Einstein-Hilbert. So I am taking a d plus 1 dimensional space-time, and this is the lambda cosmological constant, and the value of R is so now if you want to get an on-shell action, we will put this expression of R back into the Einstein-Hilbert action, and I will get now I want to write this action is in our terms of R coordinate. So first this root minus the dd plus 1x, this volume element, will break it into the angular part, into time and the radial part. So from the angular part, I will get r to the power d minus 1 omega k d minus 1, where k is 0 for planar horizon geometry, 1 for spherical horizon geometry, and minus 1 for hyperbolic horizon geometry. And now I will show the dt, how the dt integration will work. So my WDW patch is this. So this surface is corresponding R equal to R max. This surface is corresponding R equal to epsilon 0. This is also same. Okay. And I will, for symmetry, configure as it is a symmetric. So I will first.
Arpita, sorry, can I just don't use this red or
Okay,
some
sorry.
brighter side of it? Perfect.
This is visible?
Yes, it's.
So first I will compute the action for the half of the Penrose diagram, and as it is symmetric, I will just multiply by 2. So I will divide my bulk region in 3 subregions. So this one is inside the future black hole interior, like, and then 3 is the exterior region, and sorry, 2 is the exterior region, and 3 is the past interior region. So now if I am considering dt integration for region 1,
By the way, Arpita, so when you will calculate, so will you break it up in parts like t less than tc and t greater than tc, or?
Yes. So this is for t less than tc.
Okay.
So for region 1, if I take the dt integration, so t here runs from 0 to v infinity minus past. So this is the v infinity line. So this red line is v constant, which is equal to v infinity line. So this region time runs from 0 to v infinity minus r star. So for region 1, I'll get the, from time integration, I'll get v infinity minus r star, and now v infinity can be written as t plus tr plus r infinity star. So from that, I can write it as t by 2. So now if you look at region 2, so region 2, the time will go from here to here. So this lower null line is a u infinity line, and this is a v infinity line. So the region 2, for region 2, the time integration will be from u infinity plus r star to v infinity minus r star. So this will give me a time independent contribution because v minus u is just r. So r star. So and now the region 3, which is the lower part. So for that, dt will be goes from just u infinity plus r star to 0. So that is. So using this fact, we can write the bulk action for region 1, for region 2, and region 3. For region 2, we have already shown that it is not time dependent. And if we add the contributions from 1 and 3, then this plus t by 2 and minus t by 2 cancel among themselves. So ultimately we get the I bulk, which is a time independent contribution. So for this case where t less than tc, I bulk will not give any contribution to the time growth. So the I bulk O1 is so when I am doing the R integration, you can see that in the region 1, R grows from this horizon to the past future singularity, so which is epsilon 0, and so R will run from RH to R0. Then in the second region, there is R, it will run from R max is the cutoff and RH is the horizon radius, so the R will run from RH to R max, and in the third region, it will again run from RH to epsilon 0.
Sorry, eventually at the end of your calculations, you will substitute Rmax to be infinity, right? Or
yes. Rmax will go to 0, yeah. Sorry, Rmax will go to infinity.
Infinity, right?
Yeah, yeah.
Or, I mean, your answers won't finally be dependent on, I mean, what will happen to the final answer? It is
the final answer, when I'm writing dCA dt, it will not have any explicit dependence on Rmax.
Thank you.
So similarly, I can write the I bulk 3, which will be the same with just minus sign here. It will be the same, so minus sign for I bulk 3. So you can see that this plus and minus will cancel out, and then the I bulk 0 will be. Will be just the that epsilon 0 to R max. So here I will introduce the two factor because of the two-sided Penrose diagram. So total bulk action is time independent. Now I will consider the joint terms. So there will be the Gibbon-Shocking-York term will come from here, which I will denote as high future surface. Another one will come from here. And then another one will come from here, which is I cutoff. So IGHY is dependent on the trace of the extrinsic curvature, and this H is the induced metric on the boundary surfaces. So for to calculate the Gibbon-Shocking-York term, we need to define the outward directed unit normals. So we will define two normal vectors at r equal to r max. We'll define S, which is and at r equal to epsilon 0, we will define T, which is minus. So this is like the R equal to epsilon 0, this T, and R equal to this R max, this is this. And for a constant R surface, we will take the induced metric H mu nu from the original metric, and we will write the trace of extrinsic curvature. So for a ADS social black hole, we will get the K's as where D is the spatial dimension. So after this, again, now we will, so for we can carry out the integration of ddx. We will break it into the angular, radial, and time part. So radial part is 0, and for time part we will do the same kind of integration, whatever the time dependence we got. So it will be the same time integration for region 1, region 2, and region 3. So doing that, I will get the given Sawkins-York term for the future surfaces, for the past singularity surface, and for the cutoff surface. So we can show that the future surface and the past surface, they are time dependent, but the cutoff surface do not depend on time. And so, and for T greater than TC also, the contribution for my cutoff surface is same. So it will not contribute in the time evolution of complexity. So, and if we add up the future contribution, GHO contribution for the from the future singularity and the past singularity, we will get time independent thing, because of the minus T/2 is involved in past singularity, and plus T/2 you will get from the future singularity. So, this is at R equal to epsilon 0. You can see that there is no explicit time dependence. So now we'll consider the null joint contribution. So there are for T less than TC.
So Arpita, just to summarize, so far whatever you have calculated, this whatever all the calculation is di dt, whatever.
Yeah, I have till now considered only IE. I have not taken any time dependence, but I's are time independent till now, whatever I have calculated.
Right, for T less than TC, this, okay.
Yeah.
All of them are independent because this T/2 minus T/2, they are cancelling.
They are cancelling out, yeah.
Right.
So when I'll go from T greater than TC, and when the bottom vertex will go up, so at that point of time, there will be no contribution from the past singularity. So,
right. So there T/2 will remain.
Will remain, and then that will give me a time dependent contribution. And similarly, the RM, the position of the bottom vertex where two null boundaries are intersecting, that RM is also time dependent quantity, because as time goes up, this WDW patch will go upwards. So RM is time dependent. So from the RM, so the terms which will dependent on RM, they will also give me a time dependence. So we can see that for this ADS social spacetime, there is all joints are arising due to the intersection of one null boundary or null boundary and space-like boundary. So there are no cases where two space-like or two time-like boundaries are intersecting. So here we will get no Hayward joint terms. We will only calculate the null joint terms. So there are, this is one joint. another one. So first I'll consider these 4 joints. So I'll join this. Here A, which I have already introduced before, is K dot T, where K is the null normal and T is the time-like normal. So I have already introduced that T was minus dr by f epsilon 0. Now I will introduce this K. K is null, so it will have both T and R. So it is actually T plus R star. So from this we can get the joint term if we compute. So here I have multiplied with 4 because there are 4 same kind of a joints between a space like boundary and null boundary. So if I now compute I've put back the formula of FR. I am using the metric which I've used yesterday. So then this FR will be. So I'm putting back also the R equal to, I am taking this quantity at R equal to epsilon 0 and it will give me. So you can see that if you take epsilon 0 tending to 0 limit, this term vanish, this joint term vanish. And now there is another joint term. So these 4 joint terms, so whatever I consider, that's why these 4. So they are at R equal to epsilon 0. And now there will be other 4 joints, which is this 4. So for this, I will consider R equal to R max, and I will calculate the similar way. I'll get. So you can see that the joint terms for T less than Tc do not depend on term. So now if we, so now I will add all the i's and so which is, and I have denoted this as ST0. So this is 0. Which implies that for 0 less than equal to T less than equal to Tc, this where it is 0. So the next case we will consider where T is greater than Tc. So that means that at T equal to Tc, the bottom vertex of WDW patches touches the path singularity, and at T greater than Tc, the WDW patches rises up. So we'll start. And when I'll take at the late time, so So TL and TR is going to infinity. So the WDW patch will be this. So this is the last, this is the final WDW patch. So WDW patch will rise from here to this point. So T greater than TC, there will be some modifications. One modification is that the I bulk 3 will modify. So this. Because now the integration of R, previously the integration of R, the regime for integration of R was one sec. My iPad is not synchronized. One sec. इंटरनेट नहीं है. Can you guys hear me?
Yeah, we can hear you. We can see you as well. But your iPad is not in the participants list.
Yes, yes. করবো. সময় মিটিং করতে হবে তো বের করে দিয়েছে বেরিয়ে গেছে. Shubhranil, please give the permission.
Okay, you are good to go.
Yeah, so for T greater than TC, only I bulk in the third region will modify because of the integration region. Integration regime is now changed from RM to RH. So first, how I will first I will write the equation for RM. So similarly, how we describe TC, like how we define TC, that we choose the point and we match there the equal to V. So similar way here also we can do that, and we will get RM equation. So that is just matching the equal to V at this point. And now as the integration regime has changed, we will get a modified I3, which will depend on RM, and will be, for that reason, this I bulk 3 will be dependent on time. Because RM is time dependent. I bulk 1 and I bulk 2 will be the same as T less than TC case. So the extra contribution, whatever we are getting, so we will we will add this I bulk 1, 2, and 3, and we will write the difference from the T less than TC case, and we will compare the T less than TC, and we will write the difference between these two cases. So we will write I bulk as, this is the contributions from the T less than TC. I'm just continuing in the next slide. So similarly for Gibbon-Hawking York term, now there is no contribution from the past singularity. So the contribution which came from the future singularity, which are cancelling out the past singularity for the T less than TC case, now that future singularity contribution will be there. So the I surface term will be the I Gibbon-Hawking York contribution for T less than TC, and then I will get the extra contribution. You can see that now it is a time dependent contribution. And the null join contribution, the modification will be now this. So this is now a null joint, which is a joint between two null boundaries. So for this term, we have to define two null normals, which is KL and KR. So two null normals can be defined as, if I defined as KL and KR, so then KK is 0, or K and L, so LL is 0, but K dot L is a parameterization dependent. So I'll write here, I can write it as a for this point, so K, L and KR will be
Arpita, are you muted?
Yeah. So for T greater than TC, the joint term, whatever we'll get from this joint is in this form, where the time dependence will come from this Rm, and alpha square is this ambiguity. So now I want to get the time variation for this action. So I will write i's as I0 plus delta I, where I0 is for T greater than T less than TC contribution, and delta I, whatever is the contribution coming from T greater than TC part. And using the Rm equation, I can write that. So drm dt will be minus half f Rm, where dr star is dr by fr. So I'll use this relation, and now I'll vary the complexity with time. So you can see that. So I'll get delta I bulk, then I'll get the delta I surface, and then I'll get the I joint, because we have already shown that the other joint terms do not contribute in time dependence because they are time independent, which we have already shown for T less than TC case. So now when we are doing the integration, if you look at the delta I bulk, so there is a integration over 0 to Rm, and there is a explicit term of like Rd minus 1 dr, then delta T by 2 plus R star R minus R star 0. So when you are taking this kind of a time variation of this kind of expression, you will get one contribution from here, and the another contributions will come from this second part, which involves the consideration of the differentiation of Rm. So if you carry out this process, you will see that this second term will not contribute, it will ultimately cancel out the time dependence. Only the first term will give me a contribution in the time derivative. So I'll get di bulk dt is so it is a Rm dependent term. And similarly, if I do the surface term contribute. I take the surface term contributions. I also get. And for the joint term, I get a term which is proportional to log FRM by alpha square. So this alpha square will be, dependence on alpha square will be cancelled out by the boundary counter term, and there is another term which is look like a surface gravity, which is Rm F prime Rm. So now if we add these three terms and I write the dCA dt, we can show that it will be it will have just mass. So yesterday I showed that what is the mass for the uncharged ADS black hole, and then there will be the extra term which is the log term. Log. So when I am taking the boundary terms at the infinity, when it is approaches to the infinity, so the WTW patch will be this. So Rm will be now goes towards RH. And you know that F at RH is 0. So the second term will drop. So limit t tending to infinity, dc dt will be proportional to 2m by pi. And the second term will drop. So is there any confusion till now?
Yes, can you just go back to a couple of slide number 35?
Yeah.
When it merges with the space like boundary, then you are saying that Rm goes to RH, right?
And when the boundary time is at infinity, yeah.
Sorry, yeah.
Yeah.
So what happens to the log f of Rm by alpha square piece? That's
so this is a divergent quantity.
Right. It is divergent,
Yes.
right?
No, but this is multiplied with FRM, so that is 0.
Oh, okay. Oh, that's multiplied with, okay.
Yeah. Sorry. Yeah, so at the t tending to infinity, you can see dCA dt equal to 2m by pi. But now if we consider the early time where this t has just crossed Tc, so t minus Tc is very small. So that implies that Rm is also near the past singularity. So that time you can show that if you take the ADS Schwarzschild metric function, FRM will goes like and now you see if you consider this extra term, the second term in this early time region, you can see that this goes like log of some function by delta t. So you can see that this when delta t is tending to 0, this will give me a divergent term. So this is the property of CA, which I discussed on the first day, that if you consider a d greater than 3 black hole, initially till the time Tc, dCA dt will be 0. Then, and it is also minus sign. Due to minus sign, it will drops down and it is divergent here. Then numerically, if you saw, you will see that it's shoot up and then it goes to the 2m by pi limit. Sorry. Yeah. And now this, so here in the DCA-DT, this log term contributes a alpha square, which I was saying that alpha you have to, alpha is a not a fixed constant. So then your result is dependent on alpha. So then your result is not universal. So you can cancel out this alpha square contribution using the boundary counter term, which I introduced, I think. Yeah. So this was the boundary counter term. So this boundary counter term for this case will be. So we'll choose a parameterization where the lambda is r by alpha, alpha is the same alpha, and we can see the expansion will be d minus 1 by r alpha. So then after adding this boundary counter term, we can see that the DCA dt will be independent of this alpha parameter. So it will be just 1 by 2 pi, so 1 by 2m. Now the log term will modify. So we can trace out that log alpha square and it will cancel out with the boundary term, boundary counter term. And there will be another log term now will be there due to this boundary counter. So this is the final result. Here also, when you are taking this t is tending to infinity, you will get the same 2m by pi result. So alpha dependence is totally cancelled, including the boundary counter term, which ensure the reparameterization invariance. So now if you consider a charged black hole, so then the I will be just, there will be a Maxwell action added with the gravitational action. And the gravitational action, in the gravitational action, the metric function will be and the electric field will be in terms of charge. So for this case, FR will have two roots, two real roots. One will denote as R plus, which is the outer horizon, and one is at R minus, which is the inner horizon. And using the first law of black hole thermodynamics, you will compute M, T, S, Q, and mu, and then you will follow the same calculation. So now the Penrose diagram will be a little different because there are two horizons. So these are the R tending to infinity lines. These are the R plus, the outer horizon. And this is the R equal to 0 line. And the Euler-Dewitt patch will be like, so now there will be 2 RM. So there will be 2 null joints where 2 null boundaries are intersecting. So you will denote this position as RM1, where this position is RM2. And now if you calculate, now you follow the procedure what I described earlier, that you calculate the bulk action, then you add the surface terms, and then you add the joint terms. You will see that here this initial divergence, that at TC the divergence and the drop down behavior is not shown. Here the CA will go like this. So this is due to the, because here there is a mu, like there is a chemical potential is involved for the charged black hole case. So for that, so chemical potential is helping to remove the earlier behavior of CA. So this is the thing. I'll finish here today.
Okay, so let us all unmute and thank Arpita for this wonderful series of lectures. So, I mean, we do have 1 minute left of the usual time, and I was originally planning to give Arpita 5 minutes extra if need be. So we have some time for questions.
One single question. So, can you tell us or talk a bit more about why this two calculations differ? I mean, I agree that if you're calculating relative complexity, then it probably doesn't matter which one you are using. Is it a true correct statement to make? Which one to use? CV or CA?
Oh, CV and CA, the point is like the whatever I was saying, the microscopic structure is different, but asymptotic growth rate wise, it is same. So the CV and CA both asymptotes to us, saturates to a same value. But the initial behavior, like when there is a T is smaller, we can't compare CV and CA that way. So that there is a debate or there is like in literature that people wonder, there is a bias. Some people like to follow the CV because normally volume is always additive and it follows the positive energy conditions. So people like to follow CV, but for CA, if you are calculating CA, but CA it depends on that how you choose your counter term, and there are some how you choose the sign. So for the, so depending on that you will see that for the same system, if two groups of people have calculated and their calculations do not match. But for late time growth rate, everybody's calculation match. But when you are talking about only CA and you are starting the divergences, they sometimes do not match. So they depends on these notions or the signatures you are considering. So that is one problem, but CA people like to follow because of that reason that the asymptotically whatever the CA is going like 2m by pi. So this is like 2e by pi, and in quantum complexity, choosing on the number of gates and how you complete the task, there is also a growth bound on the quantum complexity, which is also proportional to 2e by pi. So some people support the CA for that reason. And another way is like for CV, normally people always calculate T greater than 0, but for CA, you can calculate for T less than 0 also. Technically, you can do that. As it is symmetric, you just can take T goes to minus T. So you will get the similar kind of results with opposite sign.
Karan has a question.
Yeah, just a comment perhaps. Like it looks to me like the CA is an averaging procedure. It's sort of like this coarse grain, fine grain sort of situation. That
yes,
if we're looking at CV, you take individual volume slices and then you can build up. CA by definition is taking the entire Wheeler-DeWitt patch. And all of these calculational techniques that you're doing, it seems to be that, I mean, at the end of the day, all these joints and the ligaments and Gibbon-Hawkins terms and all these things, what it's basically telling you is that when you have some asymmetric situation outside from the t is equal to 0 slice, it conspires to give you this RC contribution, right, after TC. And so it's basically the same information, but in a coarse-grained way. That so I think it might be that it just might be that there is this coarse-grained versus fine-grained sort of picture, and CA is a coarse-grained one. I mean, is that how you would look at it, or?
But I don't know that how, like, for classically, how can you say this coarse-grained and fine-grained thing?
Coarse-grained in the sense that it's average. So forget entropy, but like Wheeler-DeWitt patch is basically it's an integral over all the possible volumes that you have.
Yes.
Whereas
universal, yeah.
Right. So in that sense, I mean, you can call it average versus non-average. But yeah.
Hi, Arpita.
Yeah.
So I had a related but sort of unrelated as well question, which is, say, as far as I know, you personally worked on something called subsystem complexity equals to action.
Yeah.
So in that case, how do you, for example, do you compute that for a time slice, and for a subsystem, given a subsystem, how does this thing go in there?
So subsystem complexity, whatever we have calculated, that we consider the subsystem as the interior or the subsystem as the outside region. So we have considered the total action, and then we calculated the subsystem complexity for the exterior region. And we have shown that the interior action at that time, like Swingle and other people were showing that interior action is negative. So whether it was following the additivity or not, these subsystem complexities. So that was the problem. But for warp radius case, we show that these subsystem complexity is like do not depend on this sign, and its reparameterization invariant, and it's additive. So that was the thing. And subsystem we consider as like the intersection between the WDW patch and sort of a HRT surface. So HRT surface is also like you are at a boundary region, and then you are sending some light rays, and the sheet is called HRT surface. So it's like similar to the WDW patch if you are standing at TR. So they called it as an intersection of these two regions, and you calculate the individual complexity for the individual regions. And of course they are divergent. There are many divergence, logarithmic divergence and other kind of divergences are there. But ultimately we show that these subsystem complexities is following the additivity or subadditivity properties. That CA plus CA bar is greater than equal to total systems, like less than equal to total system.
So regarding this, since you mentioned HRT surfaces, is your construction particular to this exterior and interior regions of black hole, or given any HRT surface, the corresponding action region can be calculated, or Wheeler-DeWitt patch can be computed for given any sub-region?
Yes, it will be. You can calculate the complexity at any sub-region. So, but if you are saying that if you want to check these additivity properties, then you have to compare it like a whether but for WDW patch, you can see that for any point, if you are sending this null rays, that is HRT surface, and similarly that is a part of a WDW patch. Because HRT surface you are considering outside the horizon. So your results will be depend on time. So whether if you are here or here, your results will change. Obviously T greater than TC, the result will come different. It will depend on time, but the procedure is same.
Okay. So actually, if you consider, say, a one-sided black hole, and you consider this kind of actions, then it would always be a subgroup or subset of the actual Wheeler-DeWitt patch, is it?
Yes, 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 yes.
Okay.
Yeah.
So you for different subregions, but in this part, what you calculated is all of those things will be included in the thing that you calculated.
Yes, yes. Just there will be extra terms. Like if this is the subregion, so there will be extra joint terms will come from here and here. So that is the point. But like when I was taking total, these joint terms are not there.
Okay. Okay.
Yeah.
Any other questions, comments?
Yeah, is there an understanding for why CA is crossing that dotted line? Like why does CA cross the maximum bound in some sense? Is there any consensus on it?
I think people try to argue it in terms of gates which you can use in the boundary theories, but I will not be able to comment much. And it depends on that which kind of a gate set you are choosing for in the boundary theories.
The thing which worries me is like that dashed line is supposed to be like the total maximum, so to speak, information storage of the black hole, right? Or it's like T into S.
Yeah.
So
it is crossing
outside of gates and outside of everything, it still is a puzzle. Just as a geometric calculation, I think that there should be some bump which crosses that dashed line. I mean, forget complexity and everything else, right? Just the standard computation of this thing seen as a gravitational calculation. No connection to gates, nothing. Why does that bump even show up in the first place? It seems to be some kind of implicit white hole contribution, which I think is beyond what the original two-sided black hole thing which these guys were proposing.
Or
Like
there is a possibility that the boundary geometry is like when if you are calculating the boundary geometry's complexity, and if you are taking this geodesic notion of there, so maybe for this CA case it is not completely following the geodesic length is not the you have to take an average over all geodesic, or then maybe this bump will go over. But as people do not consider for this earlier time region, so they don't they just see that DCADT is positive. If the extra term which I show, that is like 2m, it is greater than 2m by pi. So that is the whether some average, there is a possibility that if you take some average over something, this bump will cancel out. But I will not be able to comment.
Yeah, because it seems to like if I'm just imagining moving that Wheeler-DeWitt patch from T0 till infinity, it seems to have a monotonic property. Like I'm just looking at the Wheeler-DeWitt patch, T is equal to 0, symmetric, should be 0, just like you've shown, and then I move it up, and it looks like there should just be a monotonic increase. But then the curve is not monotonic. It goes up, and then it comes back down, and asymptotes to some other value. So
yeah, maybe in this region there is something happening which is bumping.
Any other questions?
I have one. So apparently, as Karan was also telling, the bump going up. So let's say you have given a theory for a fixed thing. This bump, the maximum value of it is fixed, right? Is there any universality or something like that? And what can be the maximum value of CA?
No, maximum value of CA, there is no universality. There is
I mean, this bump that you are getting, is it?
It is theory dependent.
Okay.
Yeah.
It's totally theory dependent.
Yeah. Just only the asymptotic growth saturate rate to saturation, that is universal.
Okay.
Okay, I think we should thank Arpita for giving this lectures once again. So we can stop the recording now, and if people have further informal questions to ask, people can go ahead.